Yeah,
Good morning,
yes.
everybody. Thus we start our work today. But there are some changes in the program because the first co-chairman of this session will be Professor Igor Mohun instead of Professor Dogariu. And after coffee break, there are without changes. Zoom link we doesn't change from one part of this session to another part of the session. Thus, I invite Professor Igor Mohun to start our today work. Thank you.
Okay, we will begin our work because I will be instead of Professor Dogariu because it is night in Florida. So the first report is single pixel detection of structured light. The speaker is Vijay Kumar from National Institute of Technology, Varangel, India. Please.
Yeah, thank you, Professor Mukund. I suppose you can see my screen, my presentation. I have already shared.
Yes.
Thank you, thank you. Let me do the full screen. Yeah, so it's full screen now.
Yes.
Okay, thank you. Okay, so thank you. So thank you for giving me this opportunity. So I am Vijay Kumar, and I will be presenting on my work on single pixel detection. And I have slightly modified my title because this is a continuation of my last three correlation optics work. So as you can see that since 2001, when I started, after joining as a faculty at NIT Varangal, I started this work, and the first time I presented this work is obviously the correlation optics into 2021. So that this is the paper we have presented during 2021, then followed by in 2023, so which is machine learning meets singular optics. So, and there we presented our spectral-based structural light demultiplexing, and mostly it was in two-dimensional, two dimension. But here, so therefore, it is a continuation of our previous work. That's why I wanted to retain the title, and then I given a subtitle which is single pixel detection of structured light. So here we will be presenting our work. I can say more or less summary of work what we have been doing since last 5 years, and mostly focused on the current work which is single pixel detection. So let's start. So just to give you a little bit of background why we have to do this work. So as we can see that the amount of data requirement is keep on touching sky. So current time, as you can see, 2025, the current requirement is almost like a 1 petabytes per second. And there is conventional techniques cannot achieve that. So we have to go something called a space division multiplexing. So in order to understand what is space division multiplexing, as we can see that this is a very generic electromagnetic equation where all the degrees of freedom can be converted into the corresponding or multiplexing scheme. And then the space pass is left as of now unexploited. People have exploited in the multi-core fiber by using the different cores of the fiber. And here we will be focusing on the space pass. In the space pass, we can have a scalar beams as well as the vector beam. At least for this talk, I will be confining to the scalar beam only. So just to give you the phase where we have used this, so to put it in a proper context, let's consider an information. This information I will be doing multiplexing in space division multiplexing, and especially in space division multiplexing, we call it as structured light shift keying. So I will explain first that, and then we will transmit it through the fiber and space. So this technique of demultiplexing is applicable in fiber as well as space. And then we will do the demultiplexing with the technique which we have developed, which we give the name as speckle learn demultiplexing. So we can do the demultiplexing using a 2D camera, using 1D's array camera, as well as a 0D single pixel detector in temporal domain. So we will try to have a little bit of, I will try to explain how these techniques work in all the possible domain 2D, 1D and 0D. So therefore, this is the organization of TOF. First, I will tell you a little bit of structure light and structure light shift key, and then we will be focusing on the demultiplexing techniques, which is speckle based. So this I don't have to introduce to our singular optics audience. So just for the sake of completeness, I put this slide. So we have a Gaussian beam, which has a plane wave front, almost plane, and then Lagrange beam, higher order Lagrange beam, and then Hermite Gauss beam. These beams we will be using it extensively for our work, and the information we will be interested is nothing but this IL5. So we will be encoding and decoding this IL5 value. So just to, for the sake of completeness, these are the few LG beams and the corresponding LG beams. So how do we do shift key? So we have, for that, let us consider a 3-bit grayscale image. So in the 3-bit grayscale image, what I mean by that is it has 2 raised to 3 equal to 8 gray levels. So this image I can represent as 8 gray levels starting from black to white, and in between there are 8 gray levels including the top and bottom. So if I have to encode this grayscale image and send it through a binary system, I require a 3-bit, 2 raised to 3, which is 3-bit. And then these are the encoding scheme where the black, which is the total, I can assign it to 0, which will be 0, 0, 0, and the 1, the completely white, which will be nothing but 1, 1, 1, and in between values will be having corresponding value. So this is the conventional way of doing it using a binary. Then if I have to use structure light, these 8 gray levels I can assign to corresponding LG beam depending on my choice. So here we have chosen LG1 to LG8. Same thing we can do it using this HG mode as well. So each gray level we can assign to one particular HG mode. So this is the encoding scheme. So once I have encoded, what are the corresponding decoding schemes? So traditionally, just to give you a very brief introduction, so traditionally people have did this decoding and by means of interference based and diffraction based techniques. So in interference based, you just take your conventional beam, which is nothing but your plane wave, and your structure light, do the interference, and by looking at the interference pattern, we can able to distinguish. And same thing will happen in the diffraction pattern. Whatever structure light pass through the diffraction aperture, it will have far field diffraction pattern. We look at it and analyzing the far field diffraction pattern, we can able to make out which structure light being placed. So these are the traditional way of doing it in the beginning when this field has been evolved. And but this techniques has a lot of disadvantage. It can't be used in real life, I can say, scenarios. As one of the main drawbacks is the alignment. Obviously, since beam wandering will be there, beam distortion and non-scalability, I can't use the same technique for all the families of beams. So for that, people have come up, especially the internal group, Anton Zelenkov's group, they have used the machine learning, basically, nothing but the AI technique. So in the receiver end, they have used the simple CCD camera, and then they have taken the image, and that image they have fed it to a machine learning model, nothing but the computer vision. And the computer vision model, once it is trained, it is able to identify which beam is this. So this is the conventional way. Using the AI, people have used it, and then they, in the 2014, they have, I can say, reported it for the first time, and they did it for the 3 kilometer, and the same thing they have extended for the 140 kilometer in 2016. And this technique also have a disadvantage. One of the disadvantages, as you can see that these are the image based, so therefore it does not able to classify the intensity degenerate beams. We know that LG beams are intensity degenerate in the sense plus minus L will have the same intensity, only the phase is different. So that's why we can't able to recognize this because it's only the image based, and then it need to capture the whole beam profile. So it will be difficult sometimes to capture whole beam profile because as beam propagate for a long distance, it becomes very big, in aperture size become very big, and then restricted to line of sight only because wherever the beam is present, there only the information can be communicated. And then obviously it is computationally expensive because you have to take a larger beam, and then obviously if you have to do the training, it required huge data, and then it is computationally expensive. In order to overcome these techniques, we have first developed the 2D based structure like speckle based 2D in the sense the 2D camera based. So what is the idea here? The key idea is we have the structure light beam. So instead of just taking the image and then doing the demultiplexing, what we did, we have passed the structure light through a ground glass diffuser, and then we got this speckle. And these speckles look like random, but they are not obviously random. Every speckle contains the information of the corresponding beam. If for a human eye it looks, but the spatial distribution has a certain pattern which I can easily, even if I train a neural network, it can able to understand, and then based on the spectral distribution, it can understand which beam is this. That is the technique we have evolved, and in this, as you can see that I don't require the whole spectral field. A small portion of the spectral field will be enough to do the classification. Okay, so that is the idea. Instead, in contrast to the previous thing, where we have to require the whole beam, but here, if just small portion of the speckle will be enough, and here we are considering the 2D speckle, in the sense the XY domain or spatial domain, two-dimensional spatial domain we are considering for the classification. And this is our first paper where we have reported this work in JOSAI in 2022, which was presented in the 2021 correlation optics. So where the experimental is very simple, we have a Gaussian beam, then produce a LG beam using the SLM, and then pass through the ground glass, and then we have taken the far field. We can also do it from the near field to far field as well in any plane, but here we did it for the far field, and then we just took a small portion of the speckle and then trained the neural network, and neural network is able to achieve a good accuracy of less than 96%. And this work has been highlighted in optics in 2022. And then, as I said, non-linear subcommunication. So, as I said in the previous case, wherever the beam is present, there is only you can do the communication. But the advantage of speckle is it is having a broad coverage of the area. So, therefore, in this case, what we did is same thing. So, we have taken this same Bramble 3-bit image and we have encoded into the HG beams, each grayness level, and we have sent the information per pixel by pixel. So, each pixel we will first encode it. Let's say this. Completely white corresponding to 1-1, and that 1-1 mode will be, I can say, generated using the SLM, and then it is propagated through these ground glass, and this ground glass will going to scatter the beam through a larger, I can say, field of view. So in this case, we have almost like a 15-degree coverage of the field of view from the beam axis, and wherever, if we keep it, our detector, which is our 2D camera, and wherever we keep it within the range of the speckle, we can able to identify. For a proof of concept, we have capped the CCD camera at the 3 different positions, C1, C2, C3. C2 is the on axis when the ground glass is not there, and then C1 and C3 are the off axis, which is 15 degree with respect, plus minus 15 degree with respect to the on axis condition. And these are the decoded images we have got it. As we can see, on axis has given accuracy of 96, 92 off, 92 and almost 93 at the off axis. Off axis is slightly less because obviously the noise to signal ratios goes down as we go away, but at least it is good enough as a proof of concept. And this work is also has been highlighted in optics in 2023 in OPI December issues. So coming back to the do we really require the 2D spectral pattern? Since we see that our beam is azimuthally symmetric, and this azimuthally symmetry is going to give rise to the isotropic speckle pattern. So speckle pattern looks isotropic in all possible directions. So this information will be there in all possible directions. So can I able to take just 1D line profile in any direction, and then that will contain the information of where we thought of? The answer is, then we digged upon it, and then we really find the answer is yes. So we have taken a just line profile across any plane, and then so our data has been reduced drastically, and then we trained instead of training a 2D convolutional network, we have trained 1D convolutional network, and then it is able to classify. So what is the advantage we have achieved? As we can see that previously we were using 2D camera for doing the classification. Now we will be using only 1D array camera. So our data has been reduced by 1,000 times lesser data. And then obviously the trainable, the convolutional neural network which we have used, it has 32.k learnable parameter. But in our 1D case, we have used only 22.4k. So you can see 13 times less learnable parameter means less computational power I need to require. Accuracy was 100% previously, but in 1D case it has been achieved. When we reported it, it was 88, but now we can do it much better. And then obviously you can see the training time has been drastically reduced. Previously it was 500 minutes. We can do it just by 5 minutes. And that too in our normal PC, which we don't require a workstation, powerful workstation, which previously we required. That is the advantage we have achieved. And this is a proof of concept, same thing, we have did it. Just we have taken an image and then did the shift key and then passed through the diffuser and then taken a 1D line profile and then train the 1D CNN and it is able to classify it and then again decode it by the same technique as I have explained. So this is the 1D case. What about the 0D? 0D means can I do it with using a zero dimension detector? So for that, so same thing, we have a ground glass, LGB passing through a ground glass, we're going to create a speckle pattern. And then instead of looking at the whole speckle pattern across the 2 dimension or 1 dimension, we will sit at one particular point, let's say this point. And then with time, suppose this ground glass is rotating, so with time I can see that speckle fluctuates. So once the speckle fluctuates, so then within the speckle, I will sit it at one particular point, which is I call it single pixel detector. And then that single pixel detector, I will collect the data with respect to time. So you can see so now the speckle is there in the time that we're using a single pixel detector. So in our original case, where we are using the 2-dimensional detector or 1-dimensional array detector, the length is minimum we are using is 6 mm. But in using the single pixel detector, we can do the same job with a detector size of 5.86 minimum, but we have varied it for the reason we want to quantify what is the minimum amount of detector size we require to do the classification. So what we did is, this is the same thing, this is the experimental setup, so this is the laser, we produce the LG beam using the SLM and then pass through the ground glass, and then using the lens we will collimate it, and in we get the far field, and we can collect the far field using the camera as well as the fast photodiode. And this is the space-time profile of my speckle pattern, and I'm sitting at one particular point and then tracing this and then collecting the data in time. And then same thing, once the data is collected, then you train the 1D network and that will do the classification. So as I said, as I asked you the question, what is the minimum dimension of the detector I need to require? So for that, what we have did, we have varied the dimension of the detector, started from 5.86 micrometer, which is 1 × 1 pixel, which is in the beginning we have taken the image, and then from the image we have concentrated only on 1 × 1 pixel, which is almost like 5.86 length. Length of the pixel is 5.86, and then we have varied till 28.28 pixels, which is corresponding to 164 micrometer. So this is the detector dimension size, and then we also know that LG beam is varying, the LG speckle size of the LG beam varying with respect to the azimuthal order. So taking these two in consideration, I need to vary the speckle size. Sorry, I need to vary the detector size and then do the classification for all the beams. And this is the plot of the accuracies. So as you can see that on the x-axis, this is the detector size ds versus the speckle size, and then on the y-axis that is the accuracy. So as you can see that the lower the LG beam, lower the LG beam corresponding to the higher speckle size, and higher speckle size for a smaller detector sizes, it is not able to do the good classification. So smaller the spectral size, lower order did a poor job of the classification. But for the higher LG beams have the smaller speckle size, and the ratio of ds by s will goes up. That will going to give you a very good accuracies. So therefore, we arrive at the optimal, and this black line shows the overall accuracies, where we have taken the average speckle size of all these speckles, which is 36.7 micron. And then we have put a threshold. So if ds by ss is like 1, then it is give above 90% accuracy. So obviously, in order to do a very good job of the classification using a single pixel detector, the detector size versus the speckle size has to be greater than 1. Then it does a very good job. Otherwise, it will not be able to give give you a very good analysis. Just to sum up all the possible techniques, so therefore the whole summary is we can do the classification of the structured light using the speckle. We can do it by using a 2D camera, so we can collect a small section of the speckle and then train the 2D convolutional neural network. That will also do the job. And we can also do it by taking a 1D line array detector in the space domain. So I can collect the 1D speckle profile in the space domain. That will also able to do the classification. And we can also do by using a single pixel detector and taking the signal in time. So all these three techniques, therefore power of our technique is we can do the classification in all the three dimensions, which is 2D camera, 1D line array, and the 0D single pixel detector. That is the power. And then this is just to do the conclusion that since we are taking the speckle and any point or any region of the speckle will do the job, therefore it is very alignment tolerant. And it is, since it is a speckle and speckle depend on the phase, therefore it is also able to characterize the intensity degenerate beams, which was not possible beginning. And as I said, it's able to do it with all the possible detectors, 2D, 1D, and 0D. It is referenceless, so I don't need any reference. Just take the signal in all the possible domain and then just train the network. It is very high speed because, suppose as an example of a photodiodes are very high speed, so they can collect your data at the gigahertz speed. So I can do the declassification at a gigahertz speed, low computational cost, as I said, because since the data has been reduced drastically because of taking just a 1D array. So therefore, I don't require very hi-fi workstation. Even a small computer can, whatever we have it, I'm just presenting. Now I used to do that classification in my small computer. And then it is scalable to all the families of structured light, starting from LG, HG, PV. We also did it PP. I have not presented it. So even we also did it for vector beam, and we have also did it from near field to far field. It works in all the possible domain, as I said. And finally, it is also able to do non-line of sight communication, which was not possible earlier, which is having a profound effect. And additionally, we were working on quantum domain as well. So this technique I can easily apply, especially the 0D, where you are getting the photon in time. So I can able to do the classification by looking at the photon statistics, which OLB we have done. So with this, I thank you. And this is the funding. I acknowledge the funding and my past supervisors. And yeah, these are my students, which he has contributed significantly to this work, starting from Himangi to Venugopal. He has presented the work in 2021. Then Purnesh, whatever the 1D and 0D work is done by the Purnesh. And Chanika did one work which I have not presented yet. He did it from near field to far field. Nishita and Manas, they worked on the demultiplexing, which I have not presented it, especially the structural light demultiplexing, but in different domain, not in shift key. So yeah. So with this, I thank you for the opportunity. If any question is there, I will be happy to answer. Thank you.
Thank you very much for your interesting report. Question, please. So I have a question. If I understood correctly, sorry, your approach is concerned the free space optics communication.
Yes.
And can you say something about the perspective of use of your approach for the fiber link communication?
Yes. So in fiber also we did it, but I have not presented it. So in the fiber also the same similar things work. Let's say LG beam, and it is coupled to the fiber. The LG beam will going to excite the corresponding group of modes, and that modes will going to propagate inside the fiber, and then they will interfere and come out. At the end, they will interfere and give the speckle pattern. And this speckle pattern will be unique since it depends on the corresponding group of mode excited by the corresponding LG beam. Because each LG beam will be exciting a corresponding unique set of LG modes, and that will interfere at the end and is going to give you a very unique LG speckle pattern. So therefore, there is a one-to-one correspondence between the mode which you have launched into the fiber and the speckle pattern which you have got at the end. So therefore, I can do a one-to-one mapping. Once this one-to-one mapping is established, therefore, I can train by using a supervised learning algorithm, because I can map that whatever speckle pattern is there, label it with the corresponding LG mode. So therefore, I can able to identify which mode I have earlier launched into the fiber. That's the way I can clearly identify which mode I have launched it, and then I can identify which is the information I'm encoded in which particular mode. So this exactly works. Only thing is that instead of a free space, you just have to establish the one-to-one mapping between the which mode you are launching it and what speckle pattern you are getting. And the same technique follows.
Thank you.
Thank you.
Questions? Last questions. Thank you very much again for your interesting report. I see here the Professor Dogariu. Maybe you continue the session.
Thank you. Thank you. And good morning. It's my my pleasure now to introduce Etienne Brasselet to tell us about Skyrmionic beam shaping with anisotropic media. Etienne, please take it away.
Thank you. Thank you. Thank you, Aristide. All fine like this?
Yeah.
Yeah. Okay.
Yeah, we're all set.
Okay. Thank you, Aristide. Thank you, everyone, for attending. So first of all, I would like to salute all my colleagues from anywhere, and especially from Ukraine, where I wish we will all be able to attend in person in the near future. And also, I would like to apologize for those talks I'm unable to attend, as it was the case yesterday afternoon. So let me start with my presentation dealing with topologically structured light fields arising from light-matter interaction with structured anisotropic media in a broad sense, as I will explain. This work has been done in Laboratoire des Matières d'Aquitaine at University of Bordeaux in France, where we are interested in general in wave-matter interaction, and this covers not only light but also acoustic fields, and since recently surface wave fields as well. This particular talk dealing with optical skyrmions, to be specific, is an evolution of works that have been initiated together with mon cher Raphaëlien during his PhD a few years ago, and more recently followed by the PhD of Vagarchak Agopian and Moufid Chavel-Kadin, and just these days with postdoc Camila Castillo. So the structured wave-matter interaction I will deal with is related. Oh, sorry for this. Is related to is related to interaction of laser source with two kinds of structured anisotropic media. The first one will be silica glass, which has been made optically anisotropic owing to laser matter interaction, namely nanostructuring using femtosecond laser processing, leading to form birefringence that you can engineer at will. On the other end, we are dealing with self-organized anisotropic soft matter, liquid crystals, and in that case, the difference is that the topological structuring of matter emerges spontaneously depending on the geometry in which we are using the liquid crystals and the fields that they experience. So from where to start when ending with skyrmionic structures for light fields, I would say with this simple, well-known slides for our community, which deals with the generic concept of phase and polarization singularities. Just to zoom out a little bit, just to recall that phase singularities is a very generic concept that came from a simple, I would say, daily life equation. What is the time at North Pole? From which time phase singularities are emerging as shown here in a sketch. The same appear as well for polarization singularities, but for that we have to ask another question. For instance, where is the direction to the South Pole once you are sitting in a North Pole? In that case, again, looking at the meridian distribution around yourself, you will find a point where all the direction, if denoted by vectors, will meet, hence their local direction are undefined. And then this is the connection with polarization singularities. In light fields, which is one of the examples in which phase and polarization singularities emerge, if we constrain ourselves to monochromatic fields and paraxial waves, then there is an observation that one can be done, typically, for instance, from a simple computer simulation. That's combining two orthogonally polarized fields. Here, right and left circularly polarized light, depicted by these circular arrows, red and blue. If this orthogonally polarized fields contains different spatial modes, then you can obtain polarization textures when the coherent superposition of these two fields is done, as illustrated by the two polarization ellipse maps here in a given plane. These polarization textures actually can be described locally with the definition of a polarization ellipse, which is an ellipse for fully polarized fields. And every point characterized with a given polarization ellipse can be defined by a 3D vector, the Stokes vector, so the well-known vector describing in a bijective manner the polarization state, whose all options of which are covering fully and uniquely a sphere, so-called Poincaré sphere of polarization. This means that a given polarization texture, so a field of polarization ellipses, can be described by a field of a 3D vector, here, the Stokes vector, from which spatial mapping descriptions allows connecting canonical polarization ellipse distribution with, I would say, well-defined structures in other fields of physics, such as skyrmions. In that case, a given structure will be given a number, a topological invariant, which is called a scheme number, and it tells how the polarization ellipse field, so here how the field of Stokes vector, will cover the unit sphere. So in the present case here, we are dealing with a particular kind of topological structure, so of a Skyrmionic field, which is related to the Stokes field. So then we will mention them as Stokes skyrmion. 2D, because we are dealing here, as I was mentioning in a previous slide, with paraxial fields, where the polarization ellipse field is described in the transverse plane, perpendicular to the propagation direction. But those statements are quite general, and actually this vector S here, Stokes vectors, could be actually any vector field V, and the parameter space could be another one, not necessarily or spatial coordinate, X, Y, Z, but it could be abstract coordinate systems, or simply other ones like momentum space, Kx, Ky, Kz. In addition, we can move towards the description of higher dimensional topological structures by extending the description of the mapping between a given choice of a vector field mapped to a given sphere of arbitrary dimension. And these distributions exhibits some hierarchy that really embrace a large set of topological characteristics. And presently here, I will simply focus on the Stokes skyrmions in 2D. And I will further elaborate our work or experimental work towards the fabrication of devices, allowing to shape such structures. So it starts with the following. So Stokes skyrmion in the lab, you can obtain them by superimposing in a coherent manner orthogonal circular polarization states carrying well-defined modal content in terms of orbital angular momentum states, especially in the case where the special modes are the so-called Lagergos modes of indices L and P. In that case, one obtains Stokes skyrmions by construction. And to realize them experimentally, the usual way to do in the lab is to use special light modulators, which could be made with different kind of technologies, for instance, liquid crystal special phase modulators, and to split the screen of the modulator in order to shape from a given laser source here to shape two subparts that are further recombined in order to generate a given skyrmions that will be prepared on demand with appropriate shaping of a split screen special light modulator. So this approach is quite bulky and with the aim at preparing and proposing for, I would say for everyone, other kind of options to shape easily in the lab optical skyrmions. Our first steps was to realize that actually if you want to have a given field of polarization ellipse, it means, optically speaking, that you would like to shape, so it's quite straightforward statement, you want to shape a polarization ellipse point by point, which can be done, for instance, using wave plates, if you have microscopic wave plates. So you just prepare the appropriate sets of wave plates, retardants, characteristics, orientation of their optical axis, and then you will be able to shape any inhomogeneous polarization fields from a given arbitrary uniform polarization state. So to make it simple, instead of using a set of wave plates, the idea is to use a given arbitrary retarder that will allow to access from a given polarization state, a given incident polarization state, the desired output local polarization state. This can be done using a retarder, a local retarder, with the appropriate Bifurcation phase retardation, here written as the parameter capital delta, and appropriate orientation psi. Indeed, sending circular polarization state to such a retarder gives locally a response, an output field, that is a sum of orthogonally polarized circular polarization states, whose weight in terms of amplitude is driven by the retardance, delta, and whose relative dephasing is associated with the geometric phase here, 2 sigma being the helicity of incident field, times the angle psi, which is the orientation of the retarder. So, and this emerges from the known spin-orbit optical interaction here between light and structured anisotropic optical media. The point here and the difference with the usual way with split screen scalar fields is that now there is a local single screen. So it's single pixel. So locally you have a single inhomogeneous screen. And the trick to get rid of a split screen strategy is to embark another dimension. And this is a tensorial characteristic of anisotropic optics that allows to have a single screen instead of a split screen strategy. And this makes the possible realization of compact skyrmionic beam shaper possible. So let's go to the lab to show you some demonstration. But first, if you observe around you, you may find interesting optical elements, I would say. For instance, this picture, which is a glass, forks, knife, spoon, observed between cross linear polarizers, from which you can see nice sets of color and structure, which are reminiscent of stress-induced, inhomogeneous, artificial optical anisotropy. So this comes from so this structure birefringence property is simply here obtained from the material processing, how the plastic has been processed. So here you are slave of a given preparation, but the idea is to prepare on demand for a given need. And this started actually almost 2 decades ago. Now I will present a couple of slides to show from where we took our inspiration experimentally. So what I call here the early days of Stokes skyrmions. The idea is to take glass rods. And in 2007, Spielmann and Braun shown that by stressing a given glass rod appropriately, you can generate by mechanical stress on the glass rod some anisotropic structure, which is space variant, associated with a structural topological charge here, Q effective, which is -half, and a set of different phase retardation pattern that depends on the kind of stress and amount of stress you are imparting to the rod. It was not until a few years after that colleagues, Beckley, others, and Miguel, which is probably here today with us, Miguel Alonso, they identified the output field arising from such stress glass rod as a superposition of almost two pure Lagergos modes, or quasi-Lagergos modes, orthogonally polarized, sigma and minus sigma here, whose total field is generating so-called full Poincaré beam, which means a beam where all the Stokes vectors are imparted in the transverse plane. So it's full Poincaré in the sense that it covers fully the Poincaré sphere of polarization. And actually, these days, now we are renaming these full Poincaré beams as Stokes skyrmions, as they share properties with skyrmions, as I was mentioning in the introduction. And this approach was revisited more recently. First, not directly, using green lenses. The idea is that green lenses, which is graded index lenses, is a very common device in photonics, which consists of a glass rod prepared with appropriate processing to exhibit refractive index radial gradient. And there is a drawback to these optical elements that they exhibit as well residual birefringence. But this drawback can be turned into a positive point if you're interested by structured polarization state at the output. As shown here, you have a distribution radial distribution of the optical axis and associated birefringence phase retardation that leads to the possible obtention of inhomogeneous distribution for the Stokes field that share property with skyrmions. But this connections with Stokes skyrmions was made only recently, last year, by Shen and collaborators, who used green lenses and their combinations, possibly with additional optical retarders. Here in the bottom, you can see the insertion of half-wave plate between two green lenses in order to obtain experimentally, these images are experimental images, for part of the output field, well-defined Stokes skyrmionic structures, with here characterized with distinct skyrm numbers, n. Another attempt worth mentioning is the use of Q-plates, so structured azimuthally varying optical axis, half-wave plates, and which have been introduced 2 decades ago by Lorenzo Marucci and colleagues, and that are known, used quite now in a popular fashion in labs in order to shape from an input, say, Gaussian beam, circularly polarized, an output contra-circularly polarized, because it's half-wave plate retardance, which is uniform, vortex beam. Well, this is not a specially distributed Stokes field generated from the plates. However, if you detune the Q plate and set it to have a quarter wave retardance, in that case, as shown by Cardano and collaborators, this gives rise to typically, again, full Poincaré beams, and you obtain, in that case, Skyrmionic fields. However, there is an issue here, practically speaking. The issue that the modal purity is relatively bad in a sense that the set of Lagrange beams describing a given output field from a Q plate illuminated by an incident Gaussian beam, in fact, superposition of infinite number of Lagrange beams. And the special mode purities makes the observation of Stokes fields and Stokes skyrmions, only well-defined in a far field. This led us actually to revisit the Q-plate approach in this framework. The first point, before addressing the specificity of Stokes skyrmions, was to revisit the modal approach, the modal aspects of Q-plates, proposing several years ago the Lagrange modal Q-plates concept. The idea is to keep the azimuthal degree of freedom as is the case in Q-plates, in usual Q-plates, but shaping the radial degrees of freedom from radially dependent birefringent phase retardation as shown here. So analytically, you can propose a profile, a retardance profile along the radial coordinate that will impart the contra-circular output field with Lagrange mode of optimal purity. This has been realized in the subsequent years together with colleagues, especially exploiting the expertise in laser material processing from Southampton University with Peter Kazansky. They especially design synthetic silica glass in order to generate modal optics from the Lagrange point of view. But the idea is to use a femtosecond laser and to focus it. And for that, there is no need for large NA, or slightly smaller than 0.2 is enough. And to focus this into pristine silica glasses and to shape, owing to the photon flux and the incident polarization state, to shape the local form birefringence arising from local nanostructuring of silica emerging from the strong light-matter interaction in this dielectric material. With appropriate shaping and dedicated work, as done by Vagasha during his thesis, we can obtain eventually optical elements which are looking like usual retarders, but those retarders are modal retarders, and their spectral characteristics can be made monochromatic at any wavelength of your choice, but as well it can be shaped in order to exhibit rather broadband modal properties, as shown here, which was supported by analytical analysis of the light matter interaction once the device is prepared. You have here two pictures of a supercontinuum incident beam and its output modal vortex distribution simply obtained at the output of the device. So a very user-friendly approach to generate modal beams. Still, as I was mentioning before, you have to go from modal beam to modal superpositions of beam in order to shape the the polarization fields and meet any Stokes Skyrmionic demand you have. So for that, we were recently revisiting Pacharatnam's polarization control proposal, which consists in piling up 3 wave plates, namely a quarter wave plate and a half wave plate and a second quarter wave plate. So the sandwich is depicted here on the left. And this behaves as an effective wave plate whose retardance depends simply on the angle between the half wave plates and the 2 quarter wave plates in between which it is sandwiched. And the slow axis is provided with the relationship with respect to the slow axis, which is offset by pi over 4. So this was done by Pacharatnam in the context of elaborating achromatic devices. And here we exploited it regarding the effective wave plate preparation point of view. So using this approach, we were deploying the laser nanostructuring of silica glasses in 3D, not only to have a structure in the XY plane, but also to have a structure of retardance and a local optical axis along the normal to the device in order to satisfy this Pacharatnam polarization control strategy. The specific good point of this approach is that it consists with a set of retarders having constant birefringent phase retardation, which means that the average refractive index at a given point xy in the plane of the device is constant. So, which means that the dynamic phase is no longer spatially modulated as it is when using spatially varying anisotropic media, where the retardance depends in space, because this means that the average refractive index depends in space, which means that there is a dynamic phase modulation, which means that there is an unwanted, I would say, aspheric in general, dynamic phase wavefront shaping that you have to correct by, which can be done, but you have to correct by other engineering means, which is complexifying the design, even though you can achieve it as we were demonstrating. So with this strategy, I would say the multi-retarder strategy, you can obtain fully speed-controlled modal cuplates, as just reported earlier, where you can see here for either left or right incident circular Gaussian beam input, you obtained an output as an output a model pure Laguerre-Gauss beams. Whatever the charge, you just need to have the corresponding design, and that fits well with the Laguerre-Gauss shaping. So the next step is to use this for Skyrmionic beam shaping. So the idea is to combine designs and to have the appropriate designs to have the appropriate modal superposition, and then to have a Skyrmionic field that could propagate ideally from the near field to the far field. Here is an experimental realization and its computational description, where the idea is like for a given design device, we report on the Stokes analysis and simply analyze how the Stokes field is built, from which you can extract here in the region of interest the analysis of the Skyrmionic field. Here's the scheme density, which is the integrand of the scheme number integral, and which tells us that actually, yes, most certainly without much surprise, with a proper prescription of optical properties, we can obtain any prescribed Stokes field distribution for the output field that we can generalize to any order simply by adapting the designs to the needs. This leads me to present an extension of this modal cuplate strategies that that we proposed recently, earlier this year. The idea is to restart. So I'm stepping back a little bit, restarting from the Q plates associated with the winding number Q associated with the azimuthal degrees of freedom. That's why here I'm mentioning Q with a subscript phi. And that is known through spin-orbit interaction to lead to a winding number associated with the azimuthal degrees of freedom. And as we discussed before, Skyrmionic fields implies radial modulation as well. That's why we were embarking on the modal strategy. And from that, I propose to think in this way and simply add a radial winding number. What does it mean? It means that case we'll define a charge associated with the radial degree of freedom. So here it's Q with a subscript R for radial, where the idea is simply to have a well-defined amount of retardance integral from one point to another. So the center of the device up to the periphery of the device, which will be quantized according to QR, exactly in a very similar fashion as is done with Q5. In that case, what you will have a plate which is described by two indices, Q phi and QR, and with a particular design shown here, a piecewise linear design, again made from laser nanostructured silica glasses elements. You can obtain in that case structured polarization ellipse fields. But in that case, embarking a skyrmion and a Stokes skyrmions which is no longer space constrained, as it was before, where the analysis of a skyrmion has to be made in a well-defined region of space. Here, the Stokes skyrmion will be embedded in a uniform polarization field. Here is the results. These are experimental data where the skyrmionic textures at the output of this, I would say, Q phi, QR plates of different orders are obtained. We can play Q plates arithmetics to generalize it in order to obtain skyrmionic arithmetics by piling up structural wave plates in order to combine the effect of individual wave plates and generating high-order skyrmions, or using additional uniform wave plates in between different structured wave plates in order to generate multi-skyrmions whose spatial arrangement can be made linear or in a circular fashion. You can also benefit from this additional uniform wave plate strategy to rotate them, for instance, in order to rotate the generated multi-skyrmions, which means, summarizing, I would say a set of options to prepare and manipulate skyrmions at will. Still, those elements all static, and our latest developments is based on the following question. Could we have spatial light modulators with the skyrmionic feeders? So could we extend the present liquid crystal spatial light modulators playing this scalar phase to the vectorial world in order to have skyrmionic spatial light modulators? So the idea is to use liquid crystal textures as tunable devices that can be adjusted with external fields, and which is a topic on which I'm working since a while now, and that is recently summarized in this book chapter. And here is an example of recent work where we used a simple sessile liquid crystal droplet deposited on a glass, properly treated, to have a particular local optical axis orientation for the liquid crystal orientation described by the director field N, and from which you can proceed to a modeling and an analysis of what you could get by adjusting this design. The experiment is realized here with three different kinds of droplets, where the topological diversity from the skyrmionic with the skyrmionic eyes is demonstrated here with three different droplets at a given wavelength. You can extract different skyrmionic topologies here. not only a topological diversity can be achieved, but also spectral diversity. Let's say you pick up a given topology, but adjusting the radius this time for any wavelengths is also possible, and shown here in the bottom part of the slide. Now, taking benefits and taking advantage from the liquid crystal materials that is used here, you can simply use an external parameter known to change the optical properties of liquid crystals, for instance, temperature, placing the droplet in the oven, and simply tuning this temperature, the operating wavelengths at fixed topology. Reciprocally, you can fix the wavelengths and work with to do the same with voltage instead of temperature. You can also achieve topological reconfigurability at a given wavelength simply by playing over with one of these two knobs, temperature or voltage here, but you can also imagine magnetic field, for instance, or any other external stress imparted to the orientational field of the liquid crystal. Final example shown here is the use of liquid crystal film exhibiting random textures. This is old work from us, but if you turn it into taming this random texture and to obtain using a ring magnet, you embark the topology emerging from the magnetic field lines and you encode it in the nematic structure. You will obtain macroscopic defects, so this time hosted in a plate which is typically with 1 centimeter clear aperture. And by exploiting this structure, these well-defined macroscopic structures that now is turning into an optical elements and exploiting the core of this element where the retardants depend in space, then you will be able to obtain Skyrmionic structures because you play not only with the azimuthal distribution but also with the radial degrees of freedom, and you can obtain, by applying voltage to this device, either topological control of the Stokes skyrmions you obtain or the wavelength control regarding the operating wavelengths that you would like to have. All this with a single device. No longer need to change the device if you need to change topology or wavelengths. And here with a simple control parameter, the applied voltage. And this leads me to the conclusion where I would like to share two upcoming results related to advanced beam shaping. Here, embarking spatiospectral or spatiotemporal beam shaping using other kinds of liquid crystal textures. Here, a pair of topological defects that is shown to lead to tiling, Skyrmionic tiling in the spatial plane of parameters. This work being done in collaboration with Miguel Alonso. And another work in collaboration with Andrew Forbes is related to the use of this time single liquid crystal defects in a framework of quantum optics, and to exploit the spin orbit properties and tuning capabilities of liquid crystals to shape entangled photon pairs and to play with the polarization projections in order to control the Skyrmionic topology that could be, I would say, attached either to the entangled states of a pair of photons or to a given photons once one has been projected to a given well-defined spatial or spatial and polarization state. And this work is already accessible in arXiv as shown here. So I stop here. My time is over, and I thank you for your attention.
Thank you. Thank you, Etienne. Are there any questions or comments, please?
I have a question.
Please go ahead.
As I understood correctly, you can create the sum converter on the basis of glass of smooth beams for singular one for powerful radiation. Is it correct?
Yes, actually, here the robustness, the optical flux of this nanostructured silica glass optics is almost the same as with the pristine silica. So this was shown in previous work by our collaborators that the damage thresholds are roughly the same as pure silica. So yes, it's very robust.
Thank you. And the second question is, maybe I overlooked. Can you create such beam like azimuthally or radially polarized beam with your approach?
Yeah, exactly. This is, I would say, a particular case of, this is one of the particular output options that we can obtain with this kind of structured wave plates. Actually, the message is that since we can shape on demand, point by point, the polarization, the output polarization ellipse emerging from the optical elements illuminated by the uniform polarized light, it means that any kind of structures can be obtained.
Thank you.
Any other comments, questions? Please go ahead.
Hello, Michał Horski, Czernivtsi National University. Could you tell if it is possible to control using liquid crystals, skyrmions in real time in your experiments? Because I saw that you use magnetic fields, so maybe it allows to do such things in real time, or it is not possible.
So if you mean that we can, yeah, if you can change from one wavelength to another, applying an external field, for instance, temperature or here electric field, the two options I was showing, this means, and this takes typically a couple of seconds to go from one kind of shaping to another. So yes, you can follow it in real time if you like to, but the point is that you really have a modulator in the sense that you can commute by changing an external control parameter from one state to another. So far we have some limitations in terms of commuting time. I was mentioning here a couple of seconds. So we are not competing with existing liquid crystal special light modulators. State of the art goes typically up to several hundreds of hertz, let's say, or up to kilohertz for this technology. But still, here we embark this tensorial instead of scalar strategy, and we think it worth digging a bit towards possibly extending the technological capabilities of liquid crystal special light modulators.
Thank you.
Anything else? I have a quick question. Regarding the requirements for temporal coherence for the beams that you could structure with those liquid crystal features. What is the implication of having a little bit of a broader bandwidth?
Okay. So you will obtain the coherence, temporal coherence properties. They will inherit from your incident field. So you are broadening the spectrum of your incident field that you would like to shape. Then your output, let's say modal field, will be also characterized with this lowered temporal coherence just due to the broader spectrum. So from that point of view, it's not a shaping, and it's not a limitation, and it's not a reshaping of the temporal coherence as well.
No, Yeah, I understand.
And there is
Maybe we
no
can talk more. It's not about the limitation. I was just trying to figure out if there are capabilities to actually extend towards the chromatic manipulation, so to speak.
Let me find where I put the screen. Yeah, so perhaps this slide, so this slide shows that you can process at once a large set of wavelengths. So you have a broad beam, you can shape them. And then perhaps I did not catch properly your question, Aristide.
Yeah, maybe we can. I'll ask you later because we
Yeah,
are
yeah,
already
please
late.
don't contact me, no problem.
Sure. Okay. Thank you. Thank you
Thank
very
you
much
all. Thank you.
for the interesting presentation. And now we move on to the next presentation on creating beams with azimuthal polarization by means of liquid crystal and phase corrections. I am not sure who will be presenting.
Michael Vasnetsov.
All right, thank you. You're welcome to start whenever you feel comfortable.
Thank you. Well, greetings from Kiev. Do you hear me?
Yes.
Okay. My name is Mikhail Vasnetsov. And my talk is exactly about singular optics. Actually, this is an experimental work, but with some theoretical preface. The title is, you can see on the first.
No, you need to share your
I do.
presentation with us.
I do. Well, the type is as you see, and there is also an alternative title which uses the new term topological wave. I guess this is the same as the structured light, but sounds good anyway. The theoretical preface is used to explain so-called Mogen effect, which probably is not very familiar to the audience, so I will start my presentation with this.
If you don't mind to put your presentation in display mode.
Запусти презентацию.
I did. Do you see the picture with birefringence and chirality?
Yes, we see, but you can put your PowerPoint file in display mode to see it bigger.
It is now in a display mode.
Показ слайдов.
Do you see the slides coming? Or not?
We can yes, see the slides.
F5.
But it doesn't scroll.
Well, so I will use this simple mode anyway. So the first picture is a presentation how light, polarized light propagates through a birefringent medium with the anisotropic axis inclined at the angle gamma. It's very convenient for the future to use the basis with circular polarization. Coming circular polarization, say sigma plus, after this slice of the birefringence medium appears as a superposition of the same polarization with coefficient P and the orthogonal polarization sigma minus with a coefficient Q. And these coefficients are written P and Q, very simple variation. This same will appear if we use as the input polarization sigma minus. So we have this superposition as output, and we have interplay between these orthogonal polarization if both of them exist at the entrance. And we can write for them system of differential equations with the trivial solution which we know in advance. Here we see the angle gamma plays a role to change the phases. However, what we need to introduce chirality. Chirality, that is the angle of the inclination of anisotropic axis, slowly varies along the distance of propagation. And in the simplest case, is just linear function. The derived system for the differential equations will be a little bit more complicated, but the solution is simple and straightforward. Then we use this solution for the case of the initial linear polarization, which is exactly the superposition with equal amplitudes of orthogonal circular polarizations. And the angle of inclination of this linear plane of this polarization is phi. Then it's very understandable that we use that the phi equals to gamma null 0, and we will find finally the solution for the output components with this factor alpha. And in the case when the chirality factor is much smaller than the birefringence factor, we will come to the Morgan regime. And in this Morgan regime, it's very important that the initial linear polarization does rotate within the medium, keeping the plane of polarization being the same linearly polarized. It just rotates like an effect of heterotropy. And the important thing that this effect does not depend on the wavelength and on the thickness of the material. It is very promising to use this polarization rotator for the practical exploitation. The second question is, how can we get this slowly varying anisotropy? Well, it's not a problem at all if we use liquid crystals. We can orient the director of the orientation of the liquid crystal axis on one surface, on the one wall, and then rotate the opposite wall. Thus, obtain the next necessary angle of rotation. This is very easy procedure, and among the family of the twist cells, we will exploit so-called theta cell. Theta cell is composed of two walls. At one wall, we have linearly oriented liquid crystals, and the opposite wall has circular orientation. That is, coming polarization along the y-axis gradually transforms to the circular polarization and to the azimuth polarization, and thus we obtain a beam which we need with azimuth polarization. It looks fine, but one problem exists. Have a look. Starting from the 0 pi angle, we rotate the director of liquid crystals to the y-axis from 0 to pi over 2. But in the second quadrant, we rotate the director in the same direction, but from the angle minus p over 2 to 0. Along this line, along the y-axis, we will have a topological defect in the material, which is called disclination. And this topological defect will make some problems in the light passed through the material. Well, if we look just on the wall, output wall of a cell in a microscope, we will see how the polarization depends on the azimuth angle by rotation of a polarizer, and these dark sectors, they rotate as well as the rotation of the polarizer. However, an experienced eye will see some dark line. This dark line is, that I told you before, is a material defect, topological defect in material. This is disclination. What this disclination will produce in the near field? In the near field, the beam is drastically destroyed, spoiled, because a dark line, say two dark lines, or one line but with break at the center appears. The polarization is azimuthal, but in the far field, the picture will be much worse. In the far field, the beam will appear in this shape, and if we applied a polarizer in orthogonal linear polarization, we will see two structures and nothing good for the work in the same of the necessary azimuth polarization. What is the idea of this work? The idea is this work is very simple. Let us observe the direction, momentary direction of the field, electric field at the output wave. In the left half space, we see the direction follows the direction to the right. And the opposite half space, the direction of light vector is opposite. What can we do to improve the situation? Just put a pi phase retardation. In this case, all these arrows will be directed backwards, and the picture will be very nice without any phase defects, and the polarization will be exactly azimuthal. Well, we can do also radial in this case as well. What is the phase retarder that we have used? We just took a glass plate about 0.5 millimeter in thickness. This is an object plate from a microscope. and we tried several, and finally we got one, which for the wavelengths of Hini laser does produce necessary phase shift. Left picture shows the interference pattern obtained in Mach center interferometer with step on pi, and dark picture on right is a far field of a Gaussian light beam passed through the glass plate, which covers only half of its cross section. So, very simple instrument, and it will be then applied to our theta cell. This is an experimental scheme. The laser beam is collimated. Here we have our theta cell with the rubbing horizontal. Then we can introduce our glass plate as a pi-phase retarder, and we'll observe the picture in the near field and in the far field. The same picture as I have shown you before appears without phase correction, and with pi phase correction we will see that these dark lines, they disappear at all. And instead, when we had non-zero field at the center, we obtained a dark point. So it looks like we have resolved the problem. And indeed, what we observe in the far field is nearly ideal donut beam with a singularity at the center, and this is polarization singularity, and we have azimuth orientation of polarization, and we hope then to exploit this beam for the purposes of the free space communications and study the robustness in the propagation. So my short report is finalized. I thank the audience for the attention.
Thank you. Thank you very much for your presentation. Are there any comments or questions?
I have a question.
Yes, please go ahead.
I have a question. Can you return to the slide of number 5?
1, 2, 3, 4, 5.
Okay.
This.
You said that you can neglect by this term J. When this is possible?
Well, for liquid crystal, we have a difference between ordinary and extraordinary indices about from 0.1 to 0.2, and this term will be about 10 times higher than the term G, which does not exceed over our length about 100 microns, with the angle of rotation not exceeding pi over 2. This is ordinary situation for a liquid crystals like 5Cb.
Thank you. The second question is, you need the phase corrections with absolute accuracy. Have you some estimations for this?
Well, this the quality of this phase corrector can not be very high, because if you lose, say, the difference in phase will be not exactly pi, plus minus some percentage, then the quality of the output picture will be a little bit worse. But anyway, we will have a point when the field will be zero. And this point will appear probably not exactly at the center of our beam. And even just now, you can see that this shape is not absolutely round.
I see. Thank you.
Thank you.
Etienne has a
I
question.
see we have another question, Etienne.
Etienne, you must turn to.
Oh, okay, sorry. I just realized microphone was off. So thank you for your talk. I have a question about the effect of the disclination lines in the near field without the phase corrector. Whether you studied the optical structure in detail at the output regarding the phase spatial distribution and the polarization spatial distribution of this particular image as you are showing here.
This is a very interesting question, but to give a proper answer, we must return to the technique of preparation of this wall. How we do it? We have a glass plate covered with some polymer film, and then we press this glass plate to a rotating disc, which is with some material like velvet. And exactly at the center, we will not have proper orientation, because this is in some sense a singular point. And what we understood, that the orientation here give liquid crystal orientation here gives the polarization the same as along the vertical line. Probably we can do the distance between 2 points smaller, but we cannot remove it at all. And the phase difference between upper border of the dark line and the lower border is pi, in this case, in this side and in this side. What is in this point? It is open question, and it's a problem what we is working now.
Thank you.
Okay. We have one last follow-up question, please.
A little comment about the disclination. I know that disclination is the time, the defect with time dependence. In my opinion, more correctly, to call this as vector dislocation. Is it correct?
No. The disclination is a standard term for the crystals and for liquid crystals in particular. This is a line. This is a line exactly at the center between these walls, between these two walls, and the direction of rotation from one wall to another wall is not determined, or better say, the director is not rotated at all up to this declination line, then suddenly it rotates to pi over 2 and then goes to the with this orientation to the opposite side. It could be seen just in a microscope. So we have studied this, but in my report, I did not pay attention exactly to the material effects.
Thank you.
Thank you. Thank you. Thank you, all the speakers. We have a coffee break now, so please go grab your coffees. For sure, I'm gonna do it. And please let's reconvene in 30 minutes. Actually, at 11 o'clock sharp to try to stay on time.
Yeah.
Thank you.
Thank you, Professor Dogariu. Thank you, everyone, for so nice speech during this part of session. Thus, we have a coffee break at 11 o'clock Kiev time. We start another part of this session, and the co-chairman of those part will be Professor Petersen. And please don't change the links. The second part of this session has the same link. Thank you. 11 o'clock.
Okay, do we want to make
Are
a
you
start?
trying to start? Yes.
Yes. Okay, so the next speaker is Albert Ferrando from the Institute of Material Science, University of Valencia. And as you can see, the talk is Hidden Geometric Phases in Dark Ray Optics.
Okay, good morning, everybody. This work has been done, as you see, in collaboration with a PhD student of my former PhD student, Miguel Ángel García-March, Sergi de María, from the Institute of Pure and Applied Mathematics of the Polytechnic Institute of Valencia. Okay. My talk is going to deal with something in which I think all the audience is expert on, which is the trajectory of phase singularities, which is basically the trajectories of darkness, in which we analyze the zeros of the scalar field and the evolution of zero in propagation of the scalar field, as you can be seen here. And that we know that we characterize with this winding number that we call the topological charge, that tells us something about the information of the phase around this phase singularity, where we don't have, let me see if I can change this to this, yeah. About the information about the phase, but this information in general is somehow limited, right? Because not all singularities with the same charge, have exactly the same behavior. So the typically one that we like to plot is the standard canonical singularity. When you move around the phase singularity, you get a perfect linear phase, which means that basically the ladder of colors associated to phase are associated to equivalent steps, right? But in general, this is not the case, because you can have phase singularity with the same charge, in which you can see that the behavior of the phase is the same for the jump, but it's not the same, it's not linear in between. This is what differentiates a canonical singularity from a non-canonical one. And but this is something that, of course, is well known from some time ago. There are very interesting results about this question, but somehow it's not completely studied, or there are not much interest on it, despite the efforts of some authors to work on this. I want to show you that this can be really interesting by analyzing the behavior of this in the context of scalar complex field. And you see some similarities with polarization, but in fact, we're not going to talk about polarization because we're always talking about the scalar complex field. So what you can see here is what you would expect of a simple complex Taylor expansion at least in order around a phase singularity located at a complex point I call A, right? The first term will be the value of the field at the phase singularity, which is always 0. So the first leading order will be linear, either in the complex variable W or W conjugate, or X and Y. And the position at every Z of the singularity will be given by this number. So in fact, this one will be the one that will provide us with these dark ray trajectories, right? But you see the information about how this phase evolves around this is encoded in these coefficients here, C plus and C minus, if we work in the complex basis. And the evolution of this will give us information about precisely the type of way the phase behaves surrounding this singularity. So then it's very easy to check, right? And it was already seen in this paper before, that these two numbers, even if you work in the complex basis or the Cartesian basis, form a kind of a spinor, or form a spinor, in which it's very appealing that any non-canonical vortex can be considered a linear combination of a full canonical vortex with positive charge and negative canonical vortex with negative charge. So somehow we are already, seeing that we can do mathematically many things that should look familiar associated to polarization of light, despite we are talking about just scalar fields. And in fact, if we use the canonical representation in terms of X and Y components of this canonicity vector, we can provide a mapping of this spinor into a kind of Poincare, which we call canonicity sphere, in the same way in which at the node pole we will have the equivalent of linearly polarized, circularly polarized light that will, in this case corresponds to the single charge, positive charge canonical singularity, and in the south pole a negative one. As you can see here, you can also talk about canonicity ellipses, which is also known. In this language, this corresponds to, like, in the same way we generate the polarization ellipse out of the Jones vector, we can do the same trick for polarization. This theta will be just omega t, where t is time. Then here we substitute this via a standard angle running from 0 to 2 pi. And in this way, we can construct the corresponding canonicity ellipse that in fact will produce this nonlinear behavior of the phase from minus pi to 2 pi. In this way, we can see that there is a clear analogy. I'm not talking about the same thing, but we're talking something different, but it's a clear analogy between this right-handed circular light that would correspond to the node pole in polarization and a canonical vortex with positive charge, and the corresponding analogy with the left circular light in polarization and the negative charge canonical vector. On the other hand, if we analyze this as if we were analyzing the Poincare sphere, modes which lie on the equator would correspond to fields that in polarization will be linear ones, and here will correspond to kind of dipoles. We see the amplitude here. It has another line, vertical or horizontal, in which you have a jump of 0 to pi in both cases. So the complex basis for polarization is like the circular basis. The canonical basis for canonicity is equivalent of linear basis in polarization. With this, we can see here some examples of how you evolve from the canonical vortex at the North Pole. If you start to move to the south following one of these meridians this way. So you are going from here to here, to the South Pole. You can see that provided you are on the Northern Hemisphere, you get always positive topological charge of 1. You get 0 when you are in the equator, and you go to the south to change the sign. And what you're doing basically is changing the eccentricity of the corresponding ellipse. This is nice because now what we want to do, knowing that this seems to work, is to see how this evolves. In the same way, we want somehow to see if we can give a simultaneous description of the trajectory of the phase singularity and the trajectory of the associated canonicity. So basically, we want to see if for some cases we can solve the problem of what is called dimensionless 2 + 1 Schrödinger equation, that for optics, which is the case, the time, its dimensionless time can be considered a dimensionless length, propagation length, and we'll be describing the propagation length in terms of not only free propagation, you could include an harmonic gradient, like in a gradient index fiber, and even some kind of rotation of the system. This is the situation, most general situation that we will study. And we want to see if we can get information about these new degrees of freedom in this context. So because we have the possibility of solving analytically for free propagation, for example, all the trajectories of dark rays, right? But then we only have a limited information because we only can say if it has positive or negative charge. Here you have it in different colors. But I don't know much about what's going on about the canonicity along these trajectories. What we want to do is to see if it's possible, at least for some particular case. I can advance you that the general solution is not trivial and maybe too complicated, but for some particular case it's very useful and somehow can give you some surprising information. And this is the case of a single non-canonical vortex beam evolving in one of this in system like this, so with potential and with rotation. So you can prove analytically that the solution, this is not an answer, this is in fact the general form of a solution, but you can see it's parameterized in a particular way. So you can see there are like typical Gaussian behavior in which you can distinguish the standard Gaussian parameters, like the position of the Gaussian that can move. You can provide some momentum to the Gaussian as well. And you can include also a Gaussian curvature, which is a curvature, a complex symmetric matrix with positive real part, positively defined, which deals with the diffraction of the Gaussian. And the parameters that define the singularity are given here, which is the canonicity vector, which evolves in time, and this I call auxiliary complex position vector, which is related to the position of the singularity, which is not in fact the position of the singularity. And the reason is that the zeros of this function are given not by this value, but by this scalar product you can have here, right? Which is a standard scalar product, it's not a complex one, in which you can see that the position of the singularity is the result of solving the system and involves this complex field, vector field, and this canonicity field. This means that the position and the canonicity has a strong interplay, and this as we're going to see immediately. So basically what happens is that nicely you can really transform the whole solution into two types of particle-like behavior equations. One for the Gaussian involving its corresponding parameters, and other ones for the direct equations, which involve the complex position and the canonicity. And they are coupled through diffraction, so the Gaussian, the curvature matrix, the momentum, and the position of the Gaussian. And this is equivalent to solve this equation for this particular type of solution. How we find the position explicitly? As I said, this can be understood as the solution of this system of equations And this can be understood as a nonlinear projection of these two complex vectors into this two-dimensional real vector, which is given by this particular solution over here. You take these two vectors and you get the two real vectors over here using this expression over here. Now, let's see some particular cases. Let's go to see what we know, right? We consider just free propagation, no potential, no rotation. And in this case, we analyze static, symmetric Gaussian, which are centered at the origin. So you take the origin of the Gaussian, the origin of this initial singularity at the center at the origin. In that case, and for a symmetric Gaussian, so same a rotational invariant Gaussian, then what do you expect to find? Well, if you start with canonical vortex with positive charge, mass +1, you would expect to find a standard Laguerre-Gauss beam, right? And this is exactly what you obtain, because you obtain this matrix evolve like a standard diffraction, and the canonicity, the modulus, the unitary normalized canonicity to 1 does not evolve. So basically, you don't change the canonicity, and all variables of Gaussian and singularity position remain in the center. So basically, you get a straight line. So this is exactly what you expect when you solve, when you obtain a Laguerre-Gauss beam. But things start to change when you do just the small thing. I will introduce complexities step by step. If you just displace the singularity, just by the displacement of the singularity, what happens is that you still get straight dark ray propagation, but now the fact that you get initial condition which is arbitrary will change the inclination of this dark ray. So it's easy to check, as if you move the canonicity, you change the canonicity of your initial condition, of your initial singularity, the trajectories are moving. The dark ray is displaced initially, so you start here, but you see the inclination of these trajectories will change depending on the canonicity. So this is the simplest example of how canonicity can change the behavior of the trajectory. But what happens if, besides displacing, we change the symmetry of the Gaussian? So instead of having a rotational invariant Gaussian, we get kind of elliptical Gaussian with different coefficients initially for the curvature matrix. Then it's nice to see that you get also analytical solution. Now, of course, you get asymmetric diffraction, and you get also asymmetric canonicity for the two components, as well as for the complex vector. And this is telling you that since canonicity now is not conserved, you see, because the X and Y component propagates differently, when you make this projection, despite this complex vector behaves linearly, when you make the projection, the physical singularity is no longer linear. And therefore, what happens is that the canonicity moves in time, and the trajectory is no longer linear. So you can see here this type of motion that in 2D you cannot see too well, but in 3D provides this very nice picture. So basically, you start with this displaced singularity, and at the same time you see that this is forcing to bend the dark ray according to the canonicity you have at any moment. So this is displacing the singularity from the North Pole, canonicity from the North Pole to close to the equator. But if we start closer to the equator, we can get something even more interesting. Is the fact that if you're close to the equator, you move toward the south, and you are able to cross the equator, not once, but twice, as you can see here, right? You can see even better here, in which you can see the third component of the let's say, Stokes vector, that it's changing sign here and changing sign also here. And this, in fact, tells you that when you start with this displaced case with high non-canonical vortex, it starts to move towards infinity, and at the same time you get positively changed, this sign change charge moving in the same direction from minus infinity. You can see it probably better in this way. So the motion is towards you right here. So you see the phase singularity, you're moving in that direction. So the singularity is moving towards you positively. And at the same time, you see the negative one coming here. In such a way, when you move in time, you see this changing condition. In fact, this is something that has been checked experimentally in the paper I show you. They solved the problem experimentally and theoretically, so they knew theoretically this could happen, but they used a completely different mathematical framework. And it's nice to see that, in fact, in this way, we can just do the whole thing by solving these particle-like equations. Of course, we can go and making the things more complex, because the title of this talk is Hidden Geometric Phases. Of course, you can guess that we are going to talk about the hidden canonicity geometric phases, but for the moment, you see, our trajectory in the Poincare sphere is not closed. And we go to the same analogy in polarization. We know that in order to get geometrical phases, you need to have a closed circuit on top of the Poincare sphere in order to define a geometric phase that will be 1/2 of the solid angle, which is encircled by this trajectory. And it can be of two types. If you encircle the poles or not, that makes a different change of pi between one and the other. The point is, how we do this? We need to close the trajectory on this, because at the moment we only have it from here. And the question is that possible? So how we get this periodicity in the canonicity sphere? And the answer is you need to have closed dark ray trajectories. You need to have that your singularity goes back in time. This is in the XY plane, right? After some period. So you somehow, and this, because of this nonlinear projection, will provide you with this periodicity in the canonicity vector, which is the one it's required. One possibility would be to start constructing explicitly closed paths. And another possibility we can analyze here is using harmonic potentials. Because, for example, it's well known in quantum mechanics, and it's well known also in guided optics, that if you have a green multimode fiber, a graded index fiber, you can, harmonic one, you can have this periodicity ensured just by propagation. If we have this, we would expect to have this type of behavior also in the canonicity vector. And then we can use our formalism to solving this. Instead of solving the Schrödinger equation, what we do is to go to our particle-like equations, one for the Gaussian, one other for the dark rays. And then in this case, you can see first that if you don't have rotation, I'm forgetting rotation in this case, you see, interestingly enough, that the particle that represents the center of the Gaussian is, in the case of the potential, behaves just like a simple harmonic oscillator. Right? So you can see it here, right? If you look at the Dirac equations, you see that the Dirac equations, as usual, are coupled through position of the Gaussian, momentum of the Gaussian, and particularly with the diffraction curvature matrix. The point is that since the center of the Gaussian, the position of the Gaussian becomes like a harmonic oscillator, if you keep the initial solution without momentum and at the center, in any oscillator, if you don't kick it and you keep it at the center, you have no motion at all, not momentum, no motion, not changing of the position with time, which means that if you start at the at the origin, it will remain at the origin all the time. So this is zero momentum for the Gaussian at zero at the position. Therefore, this will keep the same value in time. Therefore, the direct equations keep this simple form, and even for non-asymmetric diffraction, like this one, you can get a closed, nice analytical solution for both the matrix, the curvature matrix, and for the complex n canonicity vector, which you can have here. And you see here, you get this periodicity in both cases. And we want to visualize this explicitly. And therefore, what we do is to make this nonlinear projection in order to see what we can obtain. And then we obtain this type of particular trajectory that I will show you, which has the particularity, which has a period of 2 pi, whereas now our, indeed, periodic canonicity makes a tour that takes half of the time. And in this case, we can really talk about a geometrical phase because we are encircling in the canonicity sphere finite solid angle. This can be better seen in 3-dimensional. So you can see here that how the trajectory, in fact, it's making this motion towards propagation distance. And you can see here this periodicity, the mismatch between the periodicity in canonicity and the periodicity in time or in position. You see here that this, and this are the same canonical vortex, but they are slightly displaced, right? So in order to get the same position, you need to move 2 pi, time 2 pi. Whereas in order to replicate the canonicity, you only need pi. You can see it here, you can see it always also here. So, what else you can do? Yeah. What about the case in which we started not from the North Pole, but close to the south, to the equator, and we just make this turn here, but we couldn't close it? Now, because of the potential, in fact, it's possible to close this. You cannot see it here too well, but let me show you in the 3-dimensional representation how this, as the aspect of this, you see? You can see here that the trajectory, in fact, makes this motion. You can see the third component of the canonicity vector, Stokes vector, change in time. And if you represent it, you can see here that it's similar to what we found before, but now when the positive charge goes to infinity and is replaced by the negative one, you get another replication of this, which is repeating periodically. You see, in such a way, you get this nice way of exchanging of charges during time. It's interesting that a nice way we found to visualize this using some geometric phases is that instead of using the sum of the two areas or solid angles for positive and negative, which provide the whole geometric phase, if instead of the sum, you take the difference, and you take this kind of contrast here, which is the quotient between the difference and the sum, this value, when it's 1, is telling you, when it's exactly 1, is telling you that during all propagation, the topological charge of the singularities remains always 1. 1 is -1, so it means that all the trajectory, it happens in the northern hemisphere. 1 is -1, happens in the southern hemisphere. And when it's between, somehow it's giving you information about how much, what fraction of the time the trajectory has positive charge and what fraction of the time has negative charge. Of course, and not just to finish, what would happen when we, besides potential, we introduce also rotation? Rotation is very interesting because, as we've shown in this paper, rotation, for example, in circular waveguides is providing a way of breaking time invariance. So it's like introducing a kind of effective magnetic field. So basically what tells you simply is that when you make propagation forward in the presence of this twist, forward and backward propagation are not equivalent. So basically forward goes like omega, where omega is the vector, giving you the angular rotation. And when you go backward, you get the same if you change the sign of this. So it would be interesting to see, and it's possible to study this because our formalism allows you also to study the case when you introduce a rotating frame. In order to make it different, the two cases, I will assume that we are introducing a very shallow harmonic potential. So basically, I can neglect this term. If you neglect this term, you only include rotation, what you would find here, and you start also with a canonical singularity from at the beginning, you will see that the motion of this in the canonical sphere, canonicity sphere, is something that starts to move towards asymptotically periodic trajectory, which in the asymptote will correspond to one of this type of geometrical phases that include the south, in this case, the North Pole, right? If you see the corresponding trajectory, you would see here in three-dimensional case, this is the projection. You see here that you start to move, and at some point this will kind of stabilize here. And of course, you lose periodicity because the system is not periodic, or not periodic at short distances because the potential is very shallow. But when you introduce periodicity, then of course you can get interesting results just by playing with the frequency of the rotation. So for, let's say, angular frequencies, for example, of 1, we're working with dimensionless quantities, you can see here that we can get a complete cycle of on the canonicity sphere, which has a period of pi, whereas when you look at the trajectory, this which corresponds to a trajectory of also takes pi to reproduce the same value of the canonicity. However, like happened before, when you consider this case over here, you see that a periodicity of the canonicity of pi corresponds to a periodicity of 2 pi in the real trajectory. So basically, if you look here carefully, you will see that when you make this motion over here, there are like 2 loops in the canonicity sphere. So somehow you are adding extra geometric phase to your problem associated to this particularity of combining potentials and frequency. Okay, and with this, I just make my conclusions. I hope I have convinced you that canonicity, in the way we are using, is a non-trivial intrinsic degree of freedom for phase singularities that can be important, that the canonicity formalism is analogous to polarization, that for particular case of even one single phase singularity, canonicity plays an essential in the dynamics, and that when we introduce periodic, when we introduce periodicity in the system, the canonicity and the periodicity induce hidden geometrical phases, and everything can be described using a particle-like equation of motion, at least for one single singularity. And that's all from my side, and I thank you for your attention.
That was a great talk. There's plenty of time for questions. Does anybody? I heard someone speaking earlier. You're free to speak now.
I have one comment.
Yeah.
You can pay attention to one work probably 15 years ago, we published with Professor Bikshayev. And then we show that the crossing of these dark rays reverses the signs after the crossing. And especially for the focusing of optical vortex by a cylindrical lens, this crossing is twice. If you would like, I can find this work.
Yeah, there were quite a few papers about this about 25 years ago. Like Lewis Turner was even on one.
Louis Turner was probably the same time as we did. And I remember I was a reviewer for this work of Louis Turner, and I supported it because this was the third referee. Yeah, I do remember.
Okay, thank you. Thank you. I will appreciate if you send it to me. Thank you.
I should also point out, Alberto, that that if you actually look at this, if you have, let's say, a configuration which could be in a linear or non-linear medium of a looped optical vortex, which it could either be a knot or just a loop, then obviously this ellipse structure will be closed in a way that is automatically closed. And actually and again, we wrote about that 25 years ago. That organizes a global topological hierarchy of the entire field. There are extra structures, a little bit like polarization singularities, but in the derivative structure, like your C vectors, but not vortices. And they form a very complicated topological structure that is related to knot invariance and link invariance. It organizes the topological structure of the field globally. So these are really quite general mathematical ideas. They're not just limited to the optics. And this was in the literature 25 years ago.
Okay, I'm sorry I missed it. If you can send it to me, it will be really nice.
I'll see what I can find, but it's certainly in the review that we wrote in Progress in Optics with Miles Padgett in about 2008, 2009.
Okay, but I didn't say anything. I didn't lie, right?
No, it's fine. But I'm saying that there's a lot of global stuff, and it's led to mathematicians have proved theorems about this sort of structure.
Okay, thank you.
May I make a comment?
Sure.
Yes. Hello, it's Michael Berry here. Just echoing what Mark Dennis has just said. 25 years ago, what you call non-canonical, we referred to as a core structure of a phase singularity. We called them dislocations, and we studied in great detail the statistics of the ellipticity, for example, in random waves. And this is complementing what Mark just said. Now, just another remark. I think it's confusing and unnecessary to refer to these as dark rays. There's a perfectly good terminology. They're vortex lines, optical vortex lines, or threads of darkness, as whatever you want to call them. Rays is confusing because it gives the impression of something moving along them. Now, we do have velocities associated with phase singularities, but they're the phase gradients, and they circulate faster and faster as you approach the dislocation. So you have this spiraling. So that's one comment. Now I have another comment as well. It's very difficult to change a terminology once it's established, but to refer to these vortices, a strength of them as topological charges, is fine if you're strictly in 2 dimensions. But if you're thinking, as often is the case, of plane sections of a wave in 3 dimensions, then it's very confusing to think of 2 topological charges of opposite sign coming together and annihilating, when what is actually happening is that the vortex is bent over and reverses its direction in 3 dimensions. And then the natural way to measure the strength is along the vortex direction, which is defined as the imaginary part of grad psi star cross grad psi. And it's then an artificial thing, if you have a vortex turning over, to think of it as two annihilating, because it depends on the orientation of your plane. There's often a natural paraxial direction in many cases, but still you can have small variations in this orientation of the plane, and then you think of different annihilations and creations, when really you should think of a single vortex bending over in 3 dimensions. Just some comments. I tried to clarify this already in 1998, but people still use the terminology. So these are just some comments. Otherwise, I'm just to say I liked your talk. I mean, you showed many interesting dislocation trajectories and structures.
I'm glad. Thank you. Yeah, well, just a comment on the comment. Yeah, I fully agree with you. I'm aware that in fact there's another possibility of looking at this in the 3-dimensional way, and in fact, for a particular case of one single dynamics, for one singularity, in fact, there is no generation of pairs of vortex.
Yes.
But I had some papers, and when I say that, well, my comment would be that probably what you say is very sensible in the optical context, but if I like to think of this equation as kind of general equation that can be also translated to other fields, I cannot see this kind of same behavior if you are looking with non-relativistic particles, for example, in which time is time, right? So the bending will happen in space-time, and for that, it's not that clear that this explanation, which is very natural in optics, because in optics we are just doing an approximation of something which is essentially non-paraxial, right? And then it's really a loop.
Sorry, Albert, you just solved the Gordon equation. It's just the same. It's exactly the same. There's no difference. In space-time, it's the same as time. You just have a wave function in space-time.
I know, but physically, I think it will be hard to convince someone working just with electrons in 2 + 1 dimension that there is something which is physically something moving in the space-time. It will think just it's generating.
There's been a lot of confusion in the literature, because when people are talking about electron beams, obviously they're going in both Z and time, but in a slightly different way than the light is. But everything's still just a wave function in space-time, if you like. It's just in optics we normally factor out the time.
No, it's a mathematics. I agree. I mean, the mathematics is all the same. I'm saying that it's not.
The problem might be that you have a sociological problem to convince people. That's different from a mathematical problem for what's correct.
Yeah, well, okay. I agree. I agree on that. I think you can take both if you know what you're doing. But that's the only problem. Okay, I think we are running out of time.
Yes.
So.
Well, thanks everybody. It's very interesting, high-level discussion of diffraction physics. In fairness to our next speaker, Nina Kravets, we should start soon. Nina's from the CNRS Loma University of Bordeaux in France, and the talk is titled "Magnetic Field Control Topological Charge Switching of Self-Induced Liquid Crystals."
Yeah, I hope you can hear me well and see my slides.
Yes, we can.
I'll just try to. Oh, yeah. It's been a long time that I didn't do any presentation in Zoom. Up. So yeah, I guess now you can see well my slides. Okay, so yeah, thank you so much for the introduction, and thanks to organizers for this opportunity to share the results of our work, which on the topic which I started studying in about 2017 with Etienne Brasselet. And since then, we revisit this project regularly, and we're still amazed how rich this simple system can be. And with your permission, I will go back to the generation of light with vortex phase using the liquid crystals. and namely using the self-engineered vortex masks in liquid crystals. And I will do the emphasis on the of the recent work which we've done together with a postdoc, Gregorio Gonzalez-Cortes, on the configuration of the self-engineered liquid crystal vortex plates using structured magnetic field. And I have chosen this image for the first slide, which I've taken from the website of NASA, just to indicate that I will be speaking about those vortex masks in a particular context of high contrast imaging for the astronomy called coronagraph. And so logically, I will start by just guiding you real fast through what is coronagraph. So then just to be clear what I'm speaking about. So let us imagine the telescope in this schematic representation being the ensemble of lenses and mirrors. And if we want to observe some faint objects in the vicinity of bright stars, we may encounter the problem of really huge contrast in between the brightness of the star and the objects of the faint companions of the stars. And what we actually see in the telescope is the light going from the star, passing through the entrance pupil of the telescope, which is being Fourier transformed by the lens, creating this airy disk in the sensor of the camera in the telescope. And since we want to see the faint objects in the vicinity of the star, we want to get rid of this unaxial light in the telescope. And the trick is to add some extra spiral phase to this light. And this can be done by perfectly superimposing the vortex plate with the center of this airy pattern created by the starlight. So for this, oops, how can I switch the slide? Oh yeah, excuse me. So for this, the trick is to add this vortex plate right in the center of the airy disk pattern. So we introduce this EM-phi phase into the light, and then the back Fourier transform will expel all the light, all the star light from the circular area of null intensity. So all the star light will be expelled outside, and the intensity will decrease as the power function in case of topological charge of the phase mask being equal 1. But yeah, we can use the phase masks of different charge. So then we can modify the profile of how the intensity is decreasing outside this null area. And then what we can see in the path of the telescope is that the light is expelled outside this central disk, so we can just block it using the additional washer shape secondary pupil. And then the light from the faint companions of the star, which is coming on a slightly different angle, will pass in the focal plane of the telescope at a slightly different spot, so it will be misaligned with respect to the central defect of the vortex plate. So it can still pass through the telescope, and then so then some turbulences can perturb the phase of the starlight, so it will still leak through the telescope. But using the additional dynamic mirrors, this phase perturbation can be compensated. And so then we finally can observe the airy disks of those faint companions of this star, so the exoplanets. And so just to give you the order of magnitude of the values that we are operating, I suggest that we look at this simulation reported in 2020. it's an experimental experiment. Just what if we look at our solar system from 10 parsec away? So then we will see that the Aries disk corresponding to the Earth in the vicinity of the Sun will have the contrast, will require the contrast of 10 to the order of 10, and the Aries disk will be located at about, let's say, third ring of the star Aries spot. So this indicates that we should get the huge contrast, which is being the target of the next NASA mission, which is planned for 2040 for the Habitable World Observatory. And just to indicate how far we are from there, so far the contrasts reported for the observation of the exoplanets are reaching about 10 to the order of 5, to the best of my knowledge. If I'm wrong, please correct me. And this is indicating that the requirements for those vortex plates are quite high. And so I suggest that we try to understand what parameters of those plates are important for reaching this huge contrast. So the first thing that I would like to mention is the central core size of this mask, because in math we can imagine a perfect mask. So the central singularity will be a point-like. But on the material masks, instead, during the production process, inevitably we have the central defect, which has a finite size. And so the NASA astronomers, of course, they get the access to the highly high technology and so on. So then they can get the masks with a central defect of about submicron size. And so the target indeed is to reach the sub-wavelength scale, and the similar technology can be accessible for the researchers and for less demanding applications. Let's say when we use the laser beams of about the size of 1 millimeter, so for example, not focused laser beam. The requirement for the central defect can be less strict. So, for example, the mask that we get from the same producer in our lab is of about several micrometers. So these numbers will be important for the following part of my talk. And then the other requirement for these masks is, of course, the phase delay. So I'm sure that you are all familiar with this kind of mask, but I will just go really briefly through the concept of those liquid crystal polymer-based phase masks. So the idea is to create the phase plate, the half-wave plate, with the birefringent axis structured around the center of the mask. And so here, for example, in the image A, I don't see the cursor. Yeah. So in the image A, we see the cross-polarized image of the liquid crystal polymer mask, which is basically the phase plate, the birefringent axis of which is doing one full turn. So associated topological defect is charge +1. And then if we shine the light through it, we can recognize in the image B the optical vortex, the typical Laguerre-Gaussian-like, so the donut shape beam. And in the different polarizations, so in the circular basis, we can see that left-handed and right-handed polarization components are getting the vortex phase with the topological charge, twice the topological charge of the mask. So plus or minus 1. And then the requirement, of course, is that the phase retardation associated to this mask is exactly the half-wave plate retardation. Because if it is not respected, then we get this highlighted in blue non-converted part as soon as the phase retardation is not respected. And so in principle of the vector vortex coronagraph, this will imply that the starlight is still leaking through the telescope path. And then, in case of liquid crystal, the richness of the system is, of course, associated to the fact that we can modify the birefringence of the material, and this can be done either, for example, using the temperature, as Etienne mentioned this morning in his talk, or it can be used electrically. So basically, the concept will be to reorient slightly the birefringent axis out of the plane, and then by changing the departure of the birefringent axis out of the plane, will drop the effective birefringence seen by light. So then we have those two parameters, so the birefringence and the central size of the defect, implying affecting the performance of those masks. And so far, I mentioned that those masks are made with a liquid crystal polymer. So basically, you need the technology to align the liquid crystal on the surface to secure this vortex pattern and the size of the central defect. So what we use in our team are the self-engineered structures. So basically, we just start with the liquid crystal sample with a homeotropic alignment, and we apply the electric field parallel to the initial orientation of the birefringent axis of the liquid crystal. And in case the liquid crystal has the negative negative dielectric anisotropy, the birefringent axis under the action of the electric field will go out of the plane and create spontaneously the ensemble of those material topological defects. And by chance, or by the nature of the system, the topological charge of such defects will be plus or minus 1, which is perfectly suitable for example, coronagraphy applications. And so as I said, the defects can be of a topological charge plus 1 and minus 1, and then you see that in the sample they appear on random places in the sample, dictated purely by spontaneous symmetry breaking of initial reorientation of the director. And then with the time, they attract each other and unfortunately annihilate, well, unfortunately for this kind of applications. So far, as I said, this journey of coronagraphy using the umbilic starts in 2016. Yeah, I know that the slide is quite charged with the information. Sorry for that. So on the top part of the slide, we see the report of 2016, where Etienne, with another postdoc in the team, Artur Alexanian, reported the statistics that they performed for the coronograph application using spontaneously created umbilics of the charge plus 1 and minus 1. And they successfully demonstrated that with this simple system, which requires absolutely no engineering, they could reach the contrast of about 10 to minus 3 for the coronograph performance, mimicking the star and the planet system using the laser beams. And then, as I said, the drawback of the system is that the defects appear spontaneously and then they move in the sample plane, which is not practical when you are chasing the star and try to align your telescope. So then we implemented several localization strategies, which were already known in the literature. We just applied them for the coronagraph application. So on the bottom part of the slide, you can see that we used the so-called liquid crystal light valve, being the liquid crystal cell with the photosensitive layer, indicated with orange, this BSO part, on which, by shining locally the light, we changed the electric properties of the surface, And we locally structured the electric field propagating through the liquid crystal layer. And so those green spots that we see, those green disks that are moving from the right to the left, are basically 3 spots of light that we shined on the sample in order to create locally the vortex masks and position them at will to the desired places on the sample. And so then in this image A, we can see the initial image of 3-star system mimicked by the laser light, of course. And then we could eliminate the starlight from the telescope axis, and this allowed us to observe the planet hidden somewhere in between those 3 stars. And then you see that the contrast that we could reach in this case was reaching of about 10 to minus 3, 10 to minus 4. And then we try to access we try to address the problem of what is limiting the contrast in our case, because as I said, the phase retardation could be adjusted by electric field, and this is what we were doing in order to adjust the phase retardation for these given wavelengths. But then the second part dedicated to the size of the central defect was quite limiting for us. So because we can see that in the typical regime of the electric field being close to the Frederick's threshold, the size of the defect was about 50 micrometers. And this is compatible to the airy spot that you can see in the part A of the left part of the plots. And then we demonstrated that if you exit from this usual regime of low electric fields, and then you boost your system with the high electric fields far away from Frederick's threshold, you can shrink the size of the central defect. And then, yeah, I see that the time is running, so I will accelerate. So far, I demonstrated that what we used is only the topological charge +1, and it has its intrinsic drawback being slightly squared. Don't concentrate on this, but trust me, it has an intrinsic drawback. So for years, I was asking myself, what about the -1? How can we do the -1? Because in terms of the experiment, it's quite tricky because the +1 defect can be generated by any axisymmetric additional structured field, being magnetic or electric, while the negative charge is having this hyperbolic-like structure, so it is hard to respect its 3-dimensional structure. So, inspired by work of Pavel Piransky published in 2012, we assembled a system of 4 magnets. And then, if you see at the field structure, magnetic field structure, you see that you have this hyperbolic shape. And then the trick was to introduce a slight asymmetry in this magnetic field in order to respect the torque, magnetic torque exerted on the liquid crystal director or birefringent axis, if you want. So just guiding you briefly through the final results in terms of material, by modifying the asymmetry in the magnet array that we used, we managed to switch from we managed to inscribe different topological structures in liquid crystal. The system remained quite simple. It was just 4 permanent magnets placed on the liquid crystal cell. And then this special symmetry breaking of the array of magnets was we tried to break it not only in space but also in time. Excuse me, I will skip this part. So basically, we demonstrated that we can either squeeze the system of 4 magnets spatially, or just take perfectly symmetric array of 4 magnets and translate it in time and use the fact that liquid crystals are viscous and slow in terms of reaction of varying fields. And so basically, yeah, on the right, you see the results of several different experiments that by simply translating the array of magnets, we could write different topological patterns inside the liquid crystal. And then, yeah, I'll just accelerate. And then, okay, probably I'll go through this one. And then we tried another approach. Instead of translating, rotating the array of magnets. And so basically on this slide, what I demonstrate is that with a simple system of just homeotropic liquid crystal sample and 4 permanent magnets, we could create either a vortex mask with a topological charge +1 or -1, and by setting the system into the rotation or stopping it, we could switch from one state to another, which of course could be used for the optical vortex generation purposes. And then, yeah, so on this slide, I just showed that we can switch backwards. So we can create the mask with a topological charge +1 central defect, and then easily go to the opposite one by just stopping the rotation. And yeah, I see that my time is over, so I will just skip the part about the bistability and just wrap up the presentation. So once again, this work was done in the collaboration with Etienne Brasselet and Gregorio Gonzalez-Cortes, the postdoc in the team. And in this relatively short talk, I tried to convince you that with liquid crystals and a super simple system of permanent magnets that you can buy online and just place on the top of your sample, you can create elaborated vortex masks of desired topological charge. Thank you for your attention.
Thanks, Nina. We are over time, but it would be a shame if someone has one short question with such an alluring talk, please ask it now.
I guess everyone is impatient to see the next speaker, which I totally understand.
Yes, okay. In the interest of time, it was a very great talk, Nina. We'll move on, and this will be the final talk, at least in this session. We've got Michael Berry from the University of Bristol. The talk is titled Singularities of Light, Intensity, Phase, Polarization. Thank you.
Good. Now, okay, can you see my picture? A picture?
Yes.
Yes, it's clear.
Good. Well, I've chosen to look back to a way of thinking about light that has emerged during the last half century, where instead of solving wave equations or tracing rays for particular cases of interest, for example, in applications, very, very important, we consider different levels of description, geometrical optics, scalar wave optics, polarization optics, and study the hierarchy of singularities that dominate light at each level and their interrelations. The emphasis, this is very important, will be on the singularities that are stable under perturbation, those that occur naturally, for example, without the symmetries that are so important in applications. Another theme will be natural or easily observed phenomena. But first, an application of geometrical optics that doesn't involve singularity to show that geometrical optics, even without singularities, is non-trivial. No caustics, a regime extremely simple, although not much studied. So, pre-singularity, I want to talk about Oriental magic mirrors. With the Han Dynasty in China 2,000 years ago, cast and polished bronze mirrors, slightly convex, reasonable quality. Now, on the back of the mirror is a deep cast relief pattern. And the magic, and I use the term deliberately because this was probably not intended by the manufacturers, it was observed later and then referred to as magic, is this. Instead of looking in the mirror, you shine light, for example, the sun, on it and look at the reflection on a screen or on the wall. And then you see, to your surprise, a ghostly image of the pattern on the back. Now, it was understood about a century ago that during the manufacture, casting, and grinding and polishing of the surface of the mirror, the pattern on the back is very weakly reproduced on the front, too weakly for you to see with your eye. If you look at these mirrors, then they look perfectly smooth. And I thought originally that the images were due to caustics formed by this very weak deformation of the surface mirroring what's on the back. Well, that was wrong. These variations of the surface are too weak to generate caustics, and instead the regime is what we call prefocal brightening. So the intensity on the screen at a distance z from the mirror with a surface relief h, function of position, is, and this is paraxial, which is good enough here, the Laplacian image. It's 1, that's what you'd get if it was a perfectly smooth convex mirror, plus twice the distance times the Laplacian. Now, this image, this theory, this regime is the simplest possible concentration of intensity from a varying wavefront, has a very characteristic feature that you can test. Each step has a bright edge on the low side and a dark edge on the high side. And when you, by the way, this optics automatically generates the same transformation as is used for edge detection in computer graphics. Well, you can see these bright edges and dark edges, and you can test the theory. You scan across and you see a bright and dark, you smooth it to go up and down, and then you can scan across and fit to the theory, and it's several different, almost similar fits here. I won't go into details. And from that, you can determine that the step height is about 400 nanometers. That's relief invisible to the eye, but automatically generated and very clearly visible to the eye when you reflect light from the mirror. Now, I wanted to see, after doing this work, I wanted to see these surface deformations. So I visited Peter Ade. He's somebody who tests astronomical mirrors interferometrically. So I took my mirror and we decided we would look at this region and on the back and see if it's reproduced on the front. It was surprisingly difficult because, first of all, his interferometry reproduced the overall convexity, and you couldn't see any of this detailed structure. Well, you can correct that. You can subtract off using his software, and then you see the aberrations of this convex mirror. It's not made for astronomical purposes. Well, we had to eventually subtract until we modeled the surface with a 9th order polynomial fit. And then you ghostly see the deformations on the front, which I was sure were there, but was surprisingly difficult to observe. Scanning across here, these particular asperities are about a micron in size. So that's geometrical optics when there are no singularities, pre-focal brightening. So now I get to the main point. So let's start with singularities of intensity. I like rainbows. They illustrate very many things. And one thing they illustrate is caustics. This was Descartes, 1637. Light comes in, light comes out. It comes in uniformly, it comes out concentrated. Inside the rainbow, two rays emerge in any given direction. So here's the deflection as a function of impact parameter, x. So this is a 2-to-1 map. Now, the map has a singularity when you look at the rainbow angle, deflection, and that's a caustic. It's intense. It would be infinitely intense for a given color, and if the sun were a point in geometrical optics, it's focusing. Good. 2-to-1 map. Many-to-1 map. From the sun to the lake to the eye. This is on Lake Como. Many images of the sun. There's only one sun, so it's a many-to-one map. And it's a gradient map, Fermat Hamilton. If you have the optical distance from the sun to the lake to the eye at a given instant, it depends on position on the lake, and its gradient vanishing gives you the points on the lake where you see these brilliant points. Now, the surface, you see these reflections sparkling. And, oh, sorry, excuse me. This is optical distance, this is position on the lake. These are parameters, position of the sun, time, etc. Sparkling is a succession of singularities of the map. This corresponds to caustic surfaces in the space above the water passing through your eye. And the condition there is that you've got stationarity to a higher order, the determinant vanishes. Well, the mathematics to describe this type of natural focusing was developed in the 1960s and 70s in France and Russia. It's catastrophe theory, never mind the name. The name is irrelevant in this context. And what this mathematics gives you, which was very surprising at the time, it gives you a library of caustic shapes that are stable under perturbation, classified by their codimension, the number of parameters you need to encounter the singularity. Well, the first one that occurs in the rainbow, it's called the fold catastrophe. I'm showing it in perspective in 3 dimensions, so then it will be a surface. You need one parameter to find it. Then in codimension 2, you have the cusp. It's a cusp edge in 3 dimensions. It's a cusp point in 2. Well, here are the rays, straight rays, for example, enveloping, whose envelope is a caustic. This is the cusp. Many examples, most familiar, the coffee cup, formed by reflection on the inner surface, viewed as the caustic intersects the coffee. This is a base of a water bottle, and the sun came in, it's reflected, and you see, of course, cusps everywhere. Okay, there's an artist near Bristol, Suzanne Redstone, who likes to make caustics that are illuminated by the sun. And just now, there's a glass artist, Alison Stott, fascinated by interaction of light and glass, who's produced this installation, which will appear on a wall in the physics department where I work. Here it is, and you see beautiful cusps and caustics everywhere. So very, very common. In codimension 3, well, I'll quickly show you, there's the swallowtail, the elliptic umbilic, the hyperbolic umbilic. This was unexpected at the time. I emphasize that these are the only stable shapes. Now, this theory has a predictive aspect. Look, here are the caustics focused by the waves on the surface of water, projected, viewed where the surfaces intersect the bottom of a swimming pool. Now, you see here structures, triple junctions. Now, triple junctions are nowhere in the list of stable caustics produced by this mathematics. And this told us that actually what you're seeing are blurred versions of a much more detailed structure, blurred, for example, by the half-degree width of the sun, because although they're stable under perturbation, these caustics are nevertheless quite delicate. Well, this led to some work. There are different ways in which you see a fine structure when you zoom in to laboratory-generated versions or mathematically generated versions of these triple junctions. Here are 2 impossible triple junctions, but actually they can resolve into cusp-centered triple junctions or elliptic umbilic-centered triple junctions. These these little triangles, and you see these in experiments. A spectacular example occurred in astronomy in 1976, when Mars was predicted to occult a star, Epsilon Geminorum, so that the light from this star, if you were looking at it with a telescope, would disappear and then reappear. Well, not quite, because Mars has an atmosphere which focuses light, and with the spherical Mars, the form of the focus would be a spun cusp with a focal line. Now, this spun cusp this is too far away to see, so you would expect to see inside the shadow of this star a central flash. And indeed, in the experiment, they observed this is about 6 minutes. The light from the star disappeared and reappeared, but in the middle there was this central flash. Now, this central flash, this axial focal line, is unstable. It's again not part of the list, which is telling you that with the slightest perturbation away from symmetry, this would break up into structures that are stable. Well, it's the ellipticity of Mars, which is the symmetry breaking parameter. And in fact, this unfolds into this asteroid of four cusps, and it predicts that there's fine structure in the central flash. Well, this is the prediction that in their particular observation with how the telescope moved relative to this central flash, and they predicted that this is now seconds instead of minutes, that this is what the central flash should resolve into, and it did. And I found this extremely beautiful. It's a perfect example of how a symmetry breaking perturbation generates a stable singularity. Now, you can shine a laser through some types of bathroom window glass, and you see fold caustics, you see cusp caustics, you see umbilics. Well, you also see lots of interference. So we're into waves now. And it turns out that what we learned in those years was that waves soften and decorate the caustic singularities. You've got an additional parameter, the wave number. Now, the large K asymptotics, that's when you're near geometrical optics, so you do see the caustics. For each type of singularity, labeled by a canonical optical distance function, the wave at any particular place, parameters, satisfies a scaling law. And this is a scaling law in wave number. So the wave with wave number K is the wave with wave number 1 scaled, such that an exponent beta tells you how the caustic gets more and more intense as the wavelength gets smaller and K gets larger. These exponents are shrinking exponents. They tell you how the structure of the diffraction pattern gets finer and finer, differently in different directions, generally, as the wavelength gets smaller. Now, what is this psi? It's a diffraction integral where, instead of taking the gradient of the optical distance function, we're giving the rays as stationary points, you put it up in the phase and you integrate over the variables, depending on number of dimensions that you have. Now, this tells you that a list of optical distance functions that the mathematics provides, representative normal forms for each of the different catastrophes, also gives you a list of diffraction catastrophes. And you all know the first one. They're now standard functions. They're in the digital library of mathematical functions. So, of course, we have the Airy function. We all know this, and this is a single control parameter as you cross a caustic. Here's Airy 1837. Here are the indices. Doesn't matter for this purpose to go into details. Well, you can see this on a rainbow when all of the raindrops have almost the same size. And indeed, you see a number of supernumerary rainbows, as they were called. Well, the Airy function is universal. Here is Kelvin's ship waves, and it's the Airy function across this V-shape caustic that you see. Here's another example. This the arms of this V are caustics of the rays of the water waves. Now, imagine that you're here in a small boat and a large ship passes by. Eventually, the V shape will reach you and you will feel your little boat swaying from side to side, up and down. Then you're feeling in your body the airy function that you see with your eyes when you look at supernumerary rainbows. Now, the same theory extends to tsunamis and tidal bores. Again, you have airy functions at the heart of the mathematical description, universality. Well, let's look at the cusp just very, very briefly. This is now you have two parameters, and here they are. Here's the geometrical cusp, and here's this fine intensity structure. In particular, there are zeros, which we will discuss in a little while. Now, there's a reason why I want to tell you one particular thing about the much more complicated pattern decorating the elliptic umbilic. Here's a part of the wave pattern. Well, it's integral, and there are now three parameters, x, y, and z. It's a double integral. John Nye and Francis Wright and I looked at this in great detail nearly 50 years ago, and we evaluated this integral on slices with constant z. So this is a particular slice. Okay. Well, at the first slice, where it's a point, then the diffraction pattern actually, it's explicit. It's a combination of the airy and the BI dual functions. And again, this is when you're very far. This pattern has approximate periodicity in Z as well as X and Y. It has some crystallography with a particular symmetry structure and a very rich pattern of zero lines. Well, let's take a downward slice here. Take this vertical slice. Here it is, and here it is schematically. Here's where the cusp comes. Here's where the fold comes on this side and this side. And what exists there are a pattern of rings of zeros. And these are the projections onto the XZ plane. And well, these have an interesting structure. There are rings which, after some distance beyond the cusp, become connected into a hairpin.
Очень интересно.
Sorry, somebody's talking. I don't want to. Just a second. Okay. Well, there are 14 of these rings before you get the hairpin. This is in the first row, m equals 1. So you can ask, in the mth row, how many rings are there before you get to the hairpin? Well, here's the answer. It's some interesting, totally unobvious number. And it's 14 in the first one, 34 in the second. That would be this second set of rings here, second row. And what I want, my purpose in showing this one particular result is just to point out how very rich is the reduction from waves to rays, connection between geometrical optics and wave optics, because all of this structure is stable diffraction that decorates the elliptic umbilic catastrophe. Okay, well, of course, we're thinking about waves, and of course, the characteristic feature of waves is that they possess phase. And so now we have singularities of phase, which you all here know about. I mean, a lot of concentration on these. It's much ado about nothing, if I can paraphrase Shakespeare. Complete destructive interference in a complex scalar wave. Here it is, phase chi, where the zeros, complete destructive interference, are where the intensity is 0 and the phase is undefined. They have codimension 2, so they're lines in 3 dimensions, and phase singularities, wave vortices, wave dislocations, wave nodes, the different names for the same thing. Going back to the cusp, this is the intensity. Now let's look at the phase, color-coded, and you see this rich pattern of 0 lines where all the colors meet. You can describe this analytically in great detail. Concept is much more general than the waves associated with caustics. For example, random waves. There are no caustics. You're nowhere near geometrical optics. Random waves traveling, plane waves traveling in different directions. I think 10 in this particular picture. Well, the zeros, here they are the phase singularities where all the colors meet. Very rich structure, laser speckled section of black body radiation, electron waves in a chaotic quantum dot. This is the finest scale of wave physics. This is a square wavelength. You know, one of the observations that John Nye and I made all those years ago was that really it's wrong to think that nothing much happens on sub-wavelength scales. The topological things can happen, and that's, of course, very familiar now. They were discovered, as Kosterblioch told us very beautifully yesterday, in 1833 by William Whewell in the tides. Tides are a wave of 12-hour periods circling the whole Earth, and Thomas Young suggested it would be interesting to look at what we now call the wavefronts. These are the lines where at any given time the tide is high. And he found these tideless places. Here's one of them in what was then called the German Ocean. Here is England, and here is France and Belgium. They were called amphidromic points. And these phase singularities are the stable singularities of scalar wave optics. Now, in 3 dimensions, they're lines, and they can be curved and looped. We knew that in the 1970s. I wondered for several decades whether they could also be linked and knotted. And when Mark Dennis came to work with me in the late 1990s, he produced very central ideas leading to our predictions that you can indeed create these knotted and linked phase singularities. And they were observed experimentally in the group of Miles Paget. Well, here's 2 linked phase singularities, threads of darkness, and here are not. Here is a knot. The ones that we made were had the unpleasant feature that they were threaded. We didn't want them threaded by helices of other vortex lines, these knotted threads of darkness. But Mark has pursued this and extended this work extensive in great detail and produced isolated knots that are not threaded, and there are experiments now measuring them. Okay. Singularities of polarization. Well, of course, waves are electromagnetic fields. They're not scalar waves, and you can think of the physical electric field, which is real, of course, in terms of a complex vector field with a time factor. I'm thinking of monochromatic waves. I want to make a comment about this. Of course, waves have magnetic fields as well. And I'm going to tell you about the singularity of the electric field. Well, the corresponding singularities of the magnetic field are different. And of course, you can have combinations of electric and magnetic fields, E plus IH, E minus IH. Mark has some recent insights, very general, into different possible combinations and their singularities. But electric field, good. Complex vector field, real part, vector field, imaginary part. Well, this represents, as you can read in Bon and Wolf, and this was the starting point of John Nye and Joe Heinel's work, seminal discoveries in 1987, is that the physical electric field, and you calculate it, pursues an ellipse as time increases. So this is the equation of an ellipse as time increases. And so complex vector field is a field of ellipses, as I learned from Mark, that Gibbs had discovered in the 1870s. The normal to the ellipse at any point in the field is P cross Q, imaginary part of E star cross E. And there are singularities of the ellipse field that Nye and Heinel characterized, 2 types. The first is the ellipse can degenerate into a circle. Well, then the axes of the ellipse are undefined. There's a condition for that. And there are three types of singularity. C singularity, ellipse generates into a circle, pure circular polarization. And here are the three patterns of singularity of the ellipse axes. They're points in the plane, lines in 3 dimensions, these C singularities. And then you can formula for the index is either plus or minus a half, doesn't matter, some formula involving the electric field, useful in calculations. Or the ellipse can degenerate into a line. And then line, the normal direction to the ellipse is undefined. And the patterns of the ellipse normal near the singularity, well, these are vector fields. I should have put arrows on them, I will in a moment. Index +1, index +1, index -1. And these are lines in space for 3-dimensional fields. Not obvious, they're also lines for strictly two-dimensional fields in the plane. And they're surfaces for transverse approximate fields in 3 dimensions, but think of them as lines. And again, there's a formula for the index ±1. You can easily make models. I mean, here's a little field in 3 dimensions, a particular section of it. You can look at the long axis of the polarization ellipse, and I've chosen a case where there are 2 singularities, +½ -½ these tell you the way in which these lines rotate as you rotate one time. They can be half indices, and they are, because this polarization direction is not a vector. It's a line field. So you should never represent polarization fields with arrows on them unless you put arrows in both directions. Okay, here's another field which has L singularities, lines in 3 dimensions of linear polarization, and I've chosen a particular value of Z, and what I've drawn here, now there are arrows, the projections onto this XY plane of the normal to the ellipse. Now, in nature, there's a polarization singularity whenever you look up at the sky. This is work with Mark Dennis and Raymond Lee. The blue sky, well, the very act of scattering of sunlight by air molecules polarizes the light, and to varying degrees. And you can have a pattern of polarization directions. It's linear polarization here in the sky. And these are these little line segments as measured, and also as predicted, these are the lines. Well, clearly the theory works rather well, and it's centered on unpolarized points, these black dots, and these are polarization singularities. If the polarization strength is 0, then you can't tell the direction of the lines, and these are line index half again, because we call them fingerprint singularities, because they're like the patterns of lines on your fingerprints. So fingerprints they're not vectors, they're line fields. So that's what you see. Now, the theory involves choosing a function which varies from place to place in the sky, whose zeros are these unpolarized points. And then the theory tells you that these lines tangent to the polarization direction at each place in the sky are contours of a certain elliptic integral. So there's an elliptic integral in the sky. We can't see it because we can't, except in some very rudimentary way, detect polarization. Bees can, other insects, creatures can, and it can be used as a guide to direction finding of those creatures. So polarization singularity in the sky. The first polarization singularity that I'm aware of was Hamilton in 1830, and he was thinking of biaxial crystals, transparent crystals, birefringent, biaxially symmetric, and the Fresnel wave surface is represented by the Hamiltonian in direction space. It's a polar plot. If in any direction you mark out the two refractive indices of the polarizations that can travel in that direction, and Hamilton understood its structure. It's centered on four conical intersections. We now know these are degeneracies of the reciprocal dielectric matrix as a function of direction. And here are the refractive indices, polarization directions. This is the first of several conical intersections discovered in physics and chemistry a century later. Sometimes mislabeled Dirac points, they should be Hamilton points. Now, Hamilton had a very beautiful way of seeing this structure. We called it conical refraction. There are two different types. But I want to tell you about a simpler way that we can use now using interferometry. And it's what we, Rajendra Bandari and Susanna Klein and I, called a black light sandwich. This is do-it-yourself conoscopy of the type that the mineralogists use to identify minerals. Well, you have two polarizers orthogonally arranged. This is the bread of the sandwich. And of course, it would be black if there were nothing inside. Well, there is something inside, a biaxial material. Well, such a material, those of us who are old enough to will remember, the overhead projector transparency foils we used to use to project our lectures, unaware then that they're biaxially anisotropic. So you have this sandwich, that's the filling of the sandwich. And what do you do with it? Well, as simple as possible. You just look through it at any diffuse source of light, the sky, not the sun, a white wall, a piece of white paper. Well, here's what you see if you go to the west of Ireland, where Stokes was born, and taught us so much about how to characterize polarized light. And just look out across the Atlantic with this in front of your camera, and that's what you see. Now, looking is not quite trivial. It's directing your gaze in different directions, so you're seeing the interference of the two polarizations in that particular direction at each point. And these fringes are the contours of separation of the two sheets of a cone centered on an optic axis. That's the polarization singularity that I'm drawing attention to. And I mentioned casually, just in passing, that this black stripe characterizes the is a geometric phase of pi. It's another way of describing this half-index rotation as you go around. These are linearly polarized, and the polarization rotates by pi as you go around. I'll just tell you one other little thing about this. Every point here is represented by a 2x2 matrix. Electric field EXEY comes in, electric field EXEY comes out in that direction. That's a 2x2 matrix. All of these 2x2 matrices, again, this is a little paper with Mark, are non-trivial square roots of 0. You know, ABCD multiplied by ABCD can be 0, 0, 0, 0. And all these points here are represented by matrices of that type. Well, I had a message from two Dutch astronomers saying, we've seen this structure through the windows of a train in the Netherlands. Well, where's the sandwich? The first polarized the sky itself. I've told you that the sky is polarized strongly at right angles to the sun. So here's the sun. So these are not the zeros of polarization. These are strongly polarized light. The filling of the sandwich is the window of the train, which is pre-stressed and therefore anisotropic. It's a safety thing. If there's an accident and the window shatters, it shatters into blunt cubes, not sharp splinters. What's the final polarizer? Well, like every good scientist, these Dutch astronomers carry sheets of Polaroid whenever they travel and put that in front of their eye and look through the camera. There it is. It's a very lovely thing. Now, surprisingly common. I was flying to China and looking at the moving map, and it was dinner time. So I lowered the tray table, which was covered with a hard, transparent plastic sheet. And when I saw the reflection of this moving map, I saw once again this geometric phase. So geometric phases is surprisingly common, polarization, singularities. Now, the 1830s was a miraculous decade for our subject, singular optics. There was Airy, waves near caustics, ray singularities. Whewell, 1833, in the tides, phase singularities. Hamilton, 1830, polarization singularities. All part of this subject that we now study. And to finish with, I want to point out from the most general point of view, stand back and consider the hierarchy of singularities. And the important point here is that singularities are illusions. They're illusions because at each level of physics, they get dissolved when you go to the next level, and the theory is replaced by a deeper one. Well, you've seen this. The caustic singularities of ray optics are smoothed in scalar wave optics by diffraction. And I showed you these scaling laws, which describe very precisely the type of smoothing and fine structure when you go from rays to scalar waves. But of course, scalar wave optics has its own singularities, optical vortices, where the phase is singular. Phase is the new concept introduced when you go from rays to waves. And vortices in turn disappear when you go to vector waves. There are too many components for a vector field to vanish, electromagnetic field to vanish naturally in complex vector field in 3 dimensions. And then instead you get polarization singularities. Now, of course, that's not the end of optical science. We have, of course, quantum optics. There hasn't been much discussion at this meeting of quantum optics, as I remarked yesterday, but still, the fields are also phenomena which disappear and replaced by quantum fields. So the question is, what happens to the vortices, let's just say, of scalar wave optics when you go to quantum optics? Well, quantum optics smooths the dark light of a scalar phase singularity, optical vortex, which then is a kind of window opening to our view the faint glimmering of the quantum vacuum. Optical vortices have quantum cores. Now, you consider a mode with a vortex in it and put excited atoms there. They will decay, and the intensity is dominated by stimulated emission from the mode. They see the light that's there. But of course, near a vortex, there's no light. And so then you're seeing something which additionally happens but is mostly obscured by stimulated emission. You're seeing spontaneous emission dominating. So the question is, what's the radius of the quantum core, the radius within which spontaneous emission to other unoccupied vacuum states which don't have a vortex there, what's the radius of the region where spontaneous emission dominates? And all this work was done with Mark Dennis. Again, for decades I had wondered about how quantum optics would smooth out the singularities following the two examples I've already given you. And when Mark came, again, this became clear. And here it is, the radius of the quantum core. So what's this? There's the frequency of the light, the line width of the atom you're using to detect it, and the intensity near a vortex. It's quadratic, of course. The wave varies linearly, but the intensity is quadratic. And so just as an example, we would love somebody to investigate this and measure this, because we think it's a fundamental effect. If you have a helium neon 5 milliwatt laser focused down to 100 microns, as waist size, the Gaussian beam, detected by a hydrogenic atom, well then you predict that this quantum core will be about 100 times smaller than the waist, about a micron. Well, that's in principle detectable. I expect that experimentalists would find this is not the best way to detect, but still, it's a calculation we did. Now, this is very general. If you think of sound, for example, well, sound scalar waves are models in which you assume air is a continuous fluid. Well, of course, it isn't. There's Brownian motion. And vortices in sound are fleeting threads of silence, but disturbed by the whispering of Brownian motion. And you can ask, for a given detector, a microphone, or the human eardrum, when is the smooth wave that you predict, assuming the air is a continuum, blurred by Brownian motion of the detector? We calculated that. It's if you have sound waves with wavelength lambda and loudness d decibels, well, roughly speaking, the radius of the core is the wavelength divided by 10 to the 1 plus d on 20. And for 40 decibels of 500 hertz, it's about half a millimeter. Miles Paget thinks he's measured this acoustic core. I'm not completely convinced, because it's very easy to confuse it with noise, electronic noise in the detector. But still, maybe he has. And anyway, it's a phenomenon which is worth studying in more detail. Now, I'll finish with one more quantum effect. This is with Stephen Barnett. Super kicks. You see, if you have an optical wave, psi, think of it as scalar, linearly polarized uniformly, the local momentum, which is the phase gradient actually, imaginary part of grad psi divided by psi, this gives it's a momentum, it's a canonical momentum, and it gives the mean momentum transferred to a quantum atom placed in the field, and you have a two-level atom that we use in our theory, in a transition. And well, what happens near an optical vortex? The wave goes to zero, the kick, k, goes to infinity. Now, what does that mean? It tells you something. It tells you this, that radiation pressure, what we're talking about here, deconstructs quantum mechanically near a vortex into momentum kicks that are infinitely large, k infinity, and infinitely rare. So this is an interesting prediction of how near a vortex you would expect radiation pressure to behave in what, from a classical point of view, is an anomalous way. Well, that's what I wanted to tell you. And the general philosophy was beautifully anticipated by Maxwell. It's sort of a manifesto for theoretical physics in the 1860s. In his private notebook, he wrote, "The dimmed outlines of phenomenal things all merge into one another unless we put on the focusing glass of theory and view it up first to one pitch of definition and then to another, so as to see down into different depths through the great millstone of the world. And it's optics, which is the science where, in more detail than any other branch of science, you see this idea that you can explain phenomena in different ways when you model the phenomenon at different levels, each deeper than the one before. And with that observation, I thank you very much for your attention, and I'm very pleased to be joining this lovely meeting where there are so many new discoveries being reported, so much new richness hidden away essentially in Maxwell's equations, even after 150 years. Thank you very much.
Thank you.
I'll stop sharing my screen if I can, just a moment.
Thanks for the great talk. Does anybody have any questions? I can start with the question if I'm allowed to. It's a bit pithy, but I'm thinking about the start of the talk with the start of the talk with
the mirror mirrors. Yes.
Yeah, so you had a one-to-one mapping with the Laplacian.
Yes.
Which is great because you could invert it. And then I'm wondering if you do actually form caustics because the surface is more curved, can you somehow still recover?
No, very difficult. It's very difficult. And of course, the point of this Laplacian is you hit exactly the right point. It's so simple. It's precisely because only one ray passes through each point. Because the caustics, which would start at the centers of curvature of the wavefront, are much farther away than the meter or so typically in the experiments where you observe these structures. And in fact, it could be, and I suspect I've done some estimates, that because of the overall convexity, there are never any caustics between 0 and infinity, because the curvatures of the asperities on the surface are smaller than the curvature of also very small, but sort of smaller than the curvature of the convexity of these mirrors, which typically arise during manufacture. So there are no caustics. And that's how you can invert. And of course, the inversion involves solving Poisson's equation. And although I didn't say this, an extension is to make magic windows, which is the transmission version. You can sculpt a surface invisible to the eye, such that when you shine light through it, you take it outside and let the sun shine, look on the ground, that you see a particular image that you've chosen. And to see a particular image, you have to take it solve Poisson's equation, of which this desired image is the right-hand side. And all image reconstruction processes are very difficult once you have caustics. I haven't studied it in detail, but it's because of this multivaluedness. So I think the answer is no. In general, you can't. There's no. Of course, if you know approximately the kind of object that you're looking at, that gives you a clue. Then you can, of course, model experimentally, do some various forward imaging and machine learning and all of that, and so you can train to invert. But that's not the same as an analytical inversion in which the multivaluedness occurs. So probably no.
Yes, that's what I was thinking. Thanks a lot. So with Albert Ferrando, go ahead. You've got a question.
Oh, well, I'm as usual very excited about your talk. I have a question related to something that it always puzzled me, which is the comment you made about, let's say, the quantum vacuum and the way you can relate the singularities, phase singularities with quantum vacuum, because I've been thinking about it and it's really difficult for me to visualize this in the pure quantum context, basically because if you think of it as a field theory, you should need not even quantum optics, you would need quantum field theory to make a description of it. And on the other hand, I don't know how to properly do it formally, but there's also something which vacuum is one of the most complicated puzzling objects in quantum field theory, particularly because when you say vacuum, sometimes vacuum is not vacuum, it's not empty. And for example, in QED, you can excite electron-positron pairs from vacuum, and this can produce physical effects that, in fact, I don't know how it would be possible to approach the problem of the core of phase singularity from the quantum field theory point of view, because it's hard to me to visualize it. So I was asking you, since you have started to think about it, what's the approach you and Mark are following to do it? I think it's fascinating. It's really fascinating.
Yes, I agree with that. We don't know. Of course, what I described was still a classical field, but the quantum effect on an atom placed there. But still, you need the vacuum and all of this. So it's one phenomenon. Probably there are many. We don't know how to do what you're suggesting. In particular, following the theme of this talk, would there be in quantum electrodynamics singularities? We don't know. It's a very deep question. And of course, what we don't know, even if we would find them, we wouldn't know what is smoothed by whatever is deeper than quantum electrodynamics, because that's our current best description. It's absurd to think we've reached the end, but we just don't know what's beneath quantum mechanics or quantum field theory. If there were singularities in quantum fields, this would give some clue, possibly. We don't know. So thank you very much for this comment, because it's something we've wondered about and not made progress with.
If I may just give a quick comment to just paraphrase, what we actually did in the calculation in a standard language was we used a semi-classical approximation using Einstein A and B coefficients. So obviously we sidestepped the full QED calculation, which we need to do to understand it. I mean, the standard formalism, of course, treats photons coming from quantization of the temporal parts of field modes, because that's where the energy is. Whereas you're with the vortex, which lives in the first quantization of the actual spatial position. Obviously, treating time and space quantization first and second is an idealization that probably reality doesn't care about. So what we did 20 years ago with that, people weren't quite sophisticated enough in thinking about entanglement, but thinking about the entanglement of space and time is probably would be a way using the modern tools to revisit it that goes beyond the semi-classical calculation.
Well, I think we're at time. If there's no other questions, I'll hand it over to Professor Zenko.
Okay, thank you very much. Thank you, Professor Petersen. Thank you all speakers for so nice, great presentations. And now we open our lunch, 1 hour, and we start at 2 p.m. Kiev time with second plenary session, and the co-chairman of the session will be Professor Lichinister. Thus, meet you in 1 hour. Thank you very much.
Bye.